Joe Rogan Podcast. Check it out.
The Joe Rogan Experience.
Train by day, Joe Rogan Podcast by night, all day.
I like them.
Absolutely.
It's also, there's some things that are so awesome. It's like, that's fucking awesome.
I was trying to talk about black holes to some high school students just seriously earlier this week, and I kept saying, "No, what the?" Yeah. So I got nothing to pitch, but the Shorewood Men's Club. I was giving a talk there. The Shorewood, Wisconsin, is where I live. The men's club invited me to give a talk about astronomy last week, and when I mentioned I was coming to the show, they just freaked out. And so the only thing I have is my Shorewood Men's Club water.
Well, shout out to the Shorewood Men's Club. That's awesome. That's so cool that you give those speeches. I love your YouTube talks. They're fantastic.
Oh, thank you. Wow.
I have watched probably every one you've ever done. I've watched at least, how many have you done? I've watched at least like 10 of them.
Yeah, pretty much what I did at NASA, I did a lot of sort of the science spokesperson stuff, and so most of that was, I'm more on the NASA videos. I hosted like launch events. I haven't done much privately on YouTube. I'm thinking about starting some stuff.
Oh, you should.
I'll work on that. Okay.
100%.
Thank you.
100%. You've said so many things that made me just go, what? Like, here's a big one that you said. You were talking about if the size of Earth, if the Earth was the dot of an I in a book in regular print,
yes,
that the Milky Way galaxy would be as large as the Earth itself.
Actually, a little bigger. Yeah. So, the thing is, this is an interesting thing about science communication. You say that if the sun were the size of a dot of an I, and you got to remember, you can fit 1 million Earths inside the sun, right? This is a huge thing. So if that's the size of a dot of an I on text, then the galaxy would be the size of the Earth. That's when people's eyes get big and people respond to it.
So it's not just the Earth, it's the sun. So if the sun was the dot of an eye.
Yes, that's right. So let's make this clear. So if the sun were the size of a dot of an eye on a page of text, so you could fit 1 million Earths inside that dot of an eye, then the Milky Way galaxy would be bigger than the Earth. Yeah, I think it's
so
huge.
If the Earth was the dot of an eye, then how big is the Milky Way galaxy? Because the sun is how many millions Earths?
Volume-wise, you could fit over 1 million Earths inside the sun. Yeah, yeah. The sun is about 800,000 miles across. You could fit about 110 Earths across it, the diameter.
We do those things where you show the differences between our sun and different stars, and immense stars,
yep. Mm-hmm.
And you go bigger and bigger and bigger, and you get to the point where you're like, this is not working. I can't process this. It's too kooky.
There's nobody that can process it. One of the really kind of, the thing about sort of demystifying scientists is the idea that our brains somehow work any differently. And like we can visualize what a light year is, right? A light year is about 6 trillion miles, the distance light travels in a year. No, we're human beings. We get used to using the terms. We get used to using the numbers. But we've got the same brain as everybody else. Nobody can visualize what a galaxy really is. And you can take pictures of them. You can say the word galaxy, but people have no idea what monsters these are. And then with the James Webb Space Telescope, all of a sudden you're taking pictures of billions of them. And, they're right in front of your eyes. This is not something that you can argue about. It's an image. And you see these foggy hazes of stars, basically so many stars you can't see them individually. And that's real. And it still gives me goosebumps.
That's awesome. It gives me goosebumps too, but it's so cool that it gives it to you and you actually study it your whole life.
Oh, that's the whole point. Working for NASA was a huge, huge honor. And all of us there are doing this. We were all science fiction fans. We all love imagination. That was the best thing about working at NASA was the joy and the teamwork and the camaraderie and the people that you're working with. That they think this is the best thing in the world to do.
Well, there's a real problem that we have where I think that cities and light pollution have really, it's great that we have cities. It's wonderful. It's wonderful that we have all this electricity and that we can see things at nighttime. But boy, we have done ourselves a massive disservice by not being able to see the stars all the time.
Oh, yeah.
And I think people have kind of lost the wonder of it when you're only looking at it as images on your phone, or when, the only time you get it is on vacation. Occasionally you look up in the sky, wow, look at all the stars here. It's different here. This is something that everyone should be absolutely blown away by. At night, you have a vision of the most spectacular thing any human being has ever seen ever. Just the Milky Way galaxy alone. It's nuts. It's crazy to think that those are all stars and that you can't count them. It's insane. There's so many of them, and it's above you every day, and we're just blase. We're just like so used to it. We're so dismissive. It doesn't mean anything. It's exciting when someone's excited by it, because I'm like, more people need to get the fuck away from the cities and just go see how crazy this is that we're flying through space.
Yeah. It is profound. And to be that close, I mean, just looking up, you don't even need a telescope or a pair of binoculars, the presence of something so much larger than you. But I mean, if you've listened to some of my podcasts, that I think you know that the big deal for me is that you are such a part of this. You are such an intimate, intrinsic part of this. It's not we're separate from space. We look up and there's something separate from us. That's the story of us up there. The only way the universe makes atoms, the only way that makes, the chemicals all around us, the aluminum, the iron, the oxygen, the carbon, the phosphorus, everything that makes me up. The only thing in the universe that makes atoms is the interior of a star. It's the only place where nuclear fusion puts atoms together. So everything that you are, the story is up there. And, so you're not looking at something separate and distant. Astrophysics is the story of, the end of your nose, literally. I mean, we are part of this beautiful, bigger thing.
That's a weird concept. That's from that old song, we are stardust.
Yeah, we are golden. Got to
We're
get
a
ourselves back to the garden.
carbon.
Yeah, that's right.
Yeah. That's real. That's what we are, and that's what all life is. And that's just a very strange thing for people to wrap their heads around, as we're sort of slowly getting a greater and greater understanding of the complexity of the universe itself, which is relatively recent in terms of human history. I mean, we really didn't know all what we know now because the James Webb Telescope is so crazy, where they're seeing these galaxies. They're confusing. Like, why are they formed so early?
Oh yeah. Oh, I gave a talk about those just a few weeks ago. The red dots. Yes.
Yeah.
They never let astronomers name anything. Right. You're seeing something so dramatic, and they call it the little red dots. Right. Or there's a storm on Jupiter that's 3 times the size of the Earth with 400-mile-an-hour winds, and they call it the red spot.
How come no one's allowed to name them?
Well, naming conventions, they're complex. So if you discover a comet, you get to know. If you discover an asteroid, you get to name it. If you discover a comet, the comet is named after you. But anything else has to be done by international committee. And so, they because of that, things don't end up with very interesting names. They all end up with, catalog numbers, basically phone numbers.
What do they call that weird hexagon on Jupiter? Is it a hexagon?
Saturn. The hexagon.
That's right.
I think they call that the hexagon on Saturn. They don't really the hexagonal storm. It's fantastic. You could fit about 2 Earths across that. And it's a hexagon jet stream, basically. You've got super fast moving winds around the pole of Saturn. And Saturn is so cold, the gas is so cold that there's almost no friction in the gas. So unlike here, the jet stream here, there's kind of this joke. There's a picture. Hey, that's fantastic.
That's wild.
One of my favorite pictures NASA ever took, if you look at the little dot in the middle of that, the sort of little eye of the storm, we actually have a picture from Cassini where you can see the sun glinting off of hundreds of mile high. There you go. It's down at the bottom there. It's in the bottom in the middle. Yeah, that picture. One more over. Yeah, that's a picture from the Cassini space mission. That's a real image.
Whoa.
And that's the eye of that storm. And those are, like I said, hundreds of miles high banks of clouds catching the sunlight on the poles of Saturn. And, we did that. We went there. We flew over that storm.
That's crazy.
And yeah, I mean, as amazing as the storm is, it's at least fairly well understood as a very low temperature jet stream. You may be familiar here. People kind of joke about the weather's the same. A week from now, the weather will be about the same as it is now. There are patterns that get set up in the jet stream of the Earth. and you take away all the heat and all the friction, and it forms this beautiful storm.
What is the theory is why it forms a hexagon?
It's something called a standing wave. The jet stream basically sets up a wave inside this circulation. And I will admit I'm not an atmospheric specialist, but that's what I know. And that wave kind of makes this hexagonal shape, and then you cool everything down without friction, and that's how the whole thing works. They have done computer simulations of very fast-moving jet streams under the conditions of Saturn, and you can get this sort of shape to set up.
Wow.
Yeah.
God, it's so fascinating. And it's so fascinating that we think of that as being so far away.
That's just right in our neighborhood.
It's just right there.
Yeah.
It's super hard to get to. Takes a long time, but it's just right there.
Well, we're hoping to launch, when I say we, NASA's hoping to launch a new mission to one of the moons of Saturn, hopefully in like 2028. It'll take it something like 6-7 years to get out to Saturn. But there's that giant moon of Saturn, Titan, which has a thick atmosphere. It's the only place where the air pressure is actually even a little bit greater than the room here. And it's very cold. It's almost close to 300 degrees below zero. But it's got this thick atmosphere and tons of organic molecules and evidence of liquid water below the surface. It's one of the places that might be friendly for life. And so they're designing. Have you heard about this? It's called Dragonfly. It's an octocopter. It's a big drone. There you go. Perfect. And so Dragonfly is going to be this big octocopter that we're going to land on this moon, Titan. We've already landed on this moon once with the Cassini mission. And it's got this really kick-ass chemical laboratory inside to look for the conditions for life, anything that we might be able to find, and obviously sample more than one site. Would actually fly around and go to different places. There's rain, there are oceans, there are rivers. The only place we know there are open, Great Lake-sized lakes on Titan.
Wow!
But it's so cold that it's not liquid water. It's actually liquid natural gas, liquid methane and ethane. Yeah, yeah. And again, We've already landed there. We actually sent a probe there as part of the Cassini mission to land on Titan. I mean, it's just badass that that we humans have been there. I mean, that's an artist's conception, but that's what it would look like. We sent a probe there. It took a bunch of readings and eventually froze to death. But some of the readings that it took were intriguing about the possibility of life on Titan.
Didn't the Russians land something on Venus?
Yeah, well, more than once. Yeah, the Soviet Union is the only nation, former Soviet Union now, that ever landed on Venus. And landing on Venus is way hard.
They got crazy pictures, too.
The surface temperature is about 1,000 degrees, and the air pressure is similar to being about a mile below the ocean.
That's a photo.
Yeah, it's a photo. Yep, that's real. And
it's a photo taken at 1,000-degree temperature.
Yes. Didn't last long. But everything is crushed flat. I mean, the landscape is just crushed flat by that, huge pressure, this incredible dense atmosphere. The clouds are sulfuric acid. That's why it looks yellow. That's real. Sulfuric acid clouds. I mean, it is like, classic vision of hell. It's heavy and deep and dense and sulfuric acid. Yeah.
Well, it's so interesting, too, that our understanding of planets in terms of like just what's in our solar system, they're all different. They vary so much. And this is just all we know about the known universe in terms of planets. Is it possible that there could be some planets out there that are set up completely different than the planets in our solar system?
Oh, absolutely. One of my favorite websites, just for fun, I mean, so it changes every day how many planets around other stars we know about. We call them exoplanets, exterior planets. I think we're up to about 5,000 that we know of.
When did we start noticing them?
This was
at least detecting.
Yeah. This is something I was been involved with ever since I was in college. When I was in college, my research advisor was a man named David Latham, and he was trying to find the first evidence. I mean, we figured other stars have planets. I mean, it can't be just us. But they're hard to see. They're tiny. They're dark. I mean, compared to a star, right? I mean, planets don't glow themselves, right? So they just reflect starlight. I mean, we literally said it was like trying to see a firefly around a searchlight from 200 miles away, right? How would you do it? And I mean, now we're actually getting so good at it. We find more every week, almost every day. I mean, pretty soon it's going to be, I think, thousands of new planets every single year. And
Do we have actual images?
So, for the most part, we don't have images, but that doesn't mean we don't have really cool observations, including the chemistry of their atmospheres. This is really amazing to me. So, they're so tiny, it's hard to actually get a pixel. They're smaller than a pixel. But when these things pass in front of their star, right? So, there's a star, and they pass in front of it. So you're looking at this thing pass in front of the star. It makes a tiny little solar eclipse. It goes by, it blocks a little bit of the starlight. And we find them that way. We find the stars twinkling as little planets go around them again and again. They have to come back 3 times for us to say it's a planet. Otherwise, it could be a spot on the star or something else. And the amazing thing is that the starlight will shine through the atmosphere of that planet, and we can actually probe the chemistry of the atmosphere. So we find planets that have, they're the size of the Earth, about the temperature of the Earth. They have evidence of water vapor, carbon dioxide, oxygen. And then last year there was this fantastic controversial discovery. I mean, it's very real. We need to follow it up. We think we're starting to see the evidence of organic molecules. It's not, a very strong signal yet. And this was a press release from the James Webb Space Telescope. And there were some scientists that wondered if these could be organic molecules that might someday be traceable even to the presence of life. They resembled something that plankton might give off on an ocean world. And then, of course, the rest of the scientists said the data is not good enough yet. We need much better observations before you can say that. We could maybe believe it's an organic carbon-based molecule, but we don't know which one it is yet. So, stay tuned. I would never have thought the first evidence of life outside the Earth, like really hard chemical scientific evidence, would be on a planet around another star. I thought we'd maybe find it on Mars or on some of the moons of Jupiter and Saturn. But now with the James Webb Space Telescope and the telescopes that will come afterwards, we might be able to actually, get enough of a sense of the atmosphere of these planets to start looking for life signs. Yeah.
So the sun, the star, is passing light through this little tiny thing that's smaller than a pixel.
Yeah.
And through the atmosphere where the light passes through. What are we using to detect that?
It's a technique called spectroscopy, and it's a really, really powerful thing. This is what most scientists do. As beautiful as images are of a gorgeous galaxy or a star, that's not really what we do. We look at these little squiggly lines. We get very excited. We let the light from the star pass through a grating that actually draws it into a rainbow. It takes that white light. You've seen pictures of like Prism, Dark Side of the Moon, Pink Floyd. White light goes in, rainbow comes out. If you measure really, really carefully how much light is coming in every color, you can tell astounding things. You can tell how hot the star is, how fast it's rotating, in some cases how far away a galaxy is. That's how we measure how far away they are from us in space. And you can measure the chemistry molecule by molecule. You can tell exactly what atoms and molecules are in that object. Here we go. Look at that. So what your amazing person, by the way, that's incredible. Thank you so much. Every element, carbon, nitrogen, oxygen, has a fingerprint in the rainbow. And it's like, it's that. There's nothing else like it. You know that you see carbon and nitrogen if you see these colors of the rainbow shining at that particular light. And it's not just simple things like carbon, nitrogen, oxygen, but it's water vapor, carbon dioxide, organic molecules. Everybody has their fingerprint in the rainbow. And so when the starlight shines through the atmosphere, there you go. That's how we tell what these things are made of. This is a dying star. This is actually in the Carina Nebula, and one of the most luminous stars there is. And we pass the light through a rainbow, and then looking really, really carefully at how much light comes in every color, you can pick apart exactly what it's made of.
Wow.
Yeah. Did you know that, helium, you know the element helium, right? Mm-hmm. You may be familiar that the Greek sun god's name is Helios. Helium is an element we discovered on the sun before we ever knew it was here. In the turn of the last century, in the late 1800s, when they were passing sunlight through a prism and they were looking at all these patterns of light, there was one chemical that we'd never seen before here. And so they named it after the sun, helium. It was on the sun, but not here. We never knew that helium was here. That was found later. It was later we found it, in natural gas, radioactive decay. Helium is such a light gas, it just leaves the Earth. It just doesn't stick around. And so, helium, we saw this pattern of colors in the sun's light. We were like, well, what the hell is that? And it turned out to be a new element we'd never found before.
What year was that?
We should look this up. I don't know exactly, but if we Google what year was helium found, yeah, I'm sure we can find it.
Well, I mean, I've been thinking about helium balloons and people who, suck helium and make their voice go
that's
really
right.
high-pitched.
We didn't even know about helium until
1868.
There we go.
That's nuts. So they figured out that there was helium in the sun in 1868.
Long before we ever identified it on this planet.
That is so nuts.
Yeah. Just think what's out there. We didn't even know about helium.
It's not just that it's what's out there, but that there's people out there that can figure out how to do that in 1868. Shout out to Pierre Janssen, a French astronomer who figured it out.
When you think about, I know that one thing you love is the idea of Einstein and time being different and all that. They figured all of this out around like 1908. It was more than 100 years ago. And, we don't really even have a better thing yet. They figured out that time isn't the way that we experience it just by really simple, brilliant thought processes, observations 100 and some years ago, 100 and a little more than 120 years ago. Yeah, incredible.
The idea that the faster you go, the slower time is so hard to wrap one's head around. And one of the things that I heard you were talking about GPS satellites, and you were saying that GPS satellites, because they're going about, what are they going, like 20,000 miles an hour, something like that?
So actually, if we want to break this down a little bit, there are a couple different effects about time. And one of the things that NASA does is calibrates the GPS satellites and the signal coming. And you wouldn't, I think I heard that, within a day, if we didn't take into account the time difference these things are in, that we'd be about 6 miles off. In a single day.
That's crazy.
Oh yeah, no, it's a big deal.
That's so crazy.
Yeah.
That's so crazy, and that's just above us.
Time really is something. This is not a theory. Time is variable depending on how fast you're going and also how far off the Earth's surface you are, or how far away from a big gravity body you are. In the case of the GPS satellites, there's two things going on, and it's kind of fun because it's actually the reverse for the astronauts. So if I want to break this down, this is really fun. Okay, we have clocks that are so accurate that if you move about 2 feet above where, if we had a clock on this desk, and then if we moved it up about 2 feet, we could actually detect time flowing differently because you're just that far away from the Earth's gravity, just 2 feet. Your head and your feet, we spend most of our lives, say, standing up, are actually going through time at slightly different rates. The farther away you are from a gravitational source, you probably liked movies like Interstellar, right, with Matthew McConaughey. Remember the big black hole? And the closer they get to the big black hole, the slower time goes. That's not a theory. That's something we can actually measure with clocks. And a black hole has so much gravity, it does it a lot more dramatically. But it's happening right in this room. Seriously, your head is in a different time frame than your feet right now.
That's nuts.
Yeah. And it's measurable. You need extremely accurate clocks. But in the case of the GPS satellites are in what we call a medium orbit. They're not as far away as the geostationary satellites. But they're not actually going that fast. They're only going about 9,000 miles an hour around the Earth. The astronauts in the space station, by the way, are going much faster. They're going more, let's say, approximately 20,000 miles an hour. So the GPS satellites are going a little slower. And 8,000 miles an hour is a lot, and that does slow your time down. But the bigger effect for GPS satellites is how far away from the Earth they are.
Wow.
We're actually going slower in time than they are because we're closer to the Earth's gravity. And they're so far away, they're actually going a little faster than we are in time. Now, they're also slowed down by their fast velocity. The faster you go, the slower your time goes. But people don't realize there's another factor, and that's how far away you are from gravity. For the astronauts are closer to the Earth, right? So they're actually not so far away as the satellites, and they're going much faster. So for the astronauts, it's the motion, it's the time dilation from the motion that's a bigger effect. If you are on the space station for a year, you come back about 1/100th of a second younger than you should be. And obviously that's not a big deal, but it's easily measurable.
Wow.
And in the case of the satellites, you wouldn't get the right location. The data wouldn't be right unless we take into account two things: how fast they're going. The closer to the speed of light you go, the slower time goes, but also how far away from the gravitational pull of the Earth they are. The closer you are into gravity, the slower time goes.
I think the weirdest thing that I've ever heard anybody say is that all time exists currently.
That's Einstein. I mean, that goes back 120 years.
That's such a bizarre thought.
We don't know if it's true, but it's, I mean, Einstein really thought there wasn't much of a way around it because he said, okay, well, if everything is going at different velocities compared to everything else, right? I mean, it's a great question a kid can ask. How fast am I going through space? You know, and the Earth, if you're on the equator of the Earth, that goes around at about about 1,000 miles an hour, and then, we go around the sun at about 67,000 miles an hour in our orbit. The sun's going around the galaxy about 500,000 miles an hour around the galaxy. The galaxy is going towards a galactic cluster at more than 1,000,000 miles an hour. But, how fast are we going really? And the only thing you can measure is how fast are you going relative to something else. There's no answer. How fast am I going? Well, I mean, am I still or am I actually traveling close to the speed of light right now? I don't know. So Einstein said the only way he could really think about how that would work is if the universe was just one big thing. All of time and space exists in a big whole thing. There's only one now. Einstein famously said, the past, present, and future are, persistently annoying illusions. Now, again, do we know this to be true? At the moment, we don't have any better physics, and I doubt the physics will get any less weird than that. But I mean, that's sort of the way modern physics thinks the universe may be, is a big whole thing that started from beginning to end and is all now-ish.
But if that's the case, so subjectively we can measure things. We can measure time. But what are we measuring? If it's, are we making artificial time constraints? Are we doing it ourselves? When we create a clock, we create a watch, and the watch is 24 hours a day. It's running. What is it measuring? Yeah, right. That is exactly the question Albert Einstein asked. That is a deep, excellent question. And so that was the problem. I mean, in a famous thought experiment, Einstein made a clock by setting up two mirrors and having light bounce between the two mirrors. And that was the tick of the clock. Tick, 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 tick. And the problem was that that's how he started thinking about the speed of light, is that if you had this thing in a spaceship that was going a huge fraction of the speed of light, then a person standing watching it go by would actually watch the light kind of trace out a pattern like this. Because it's actually ticking between the mirrors, but the mirrors are moving along. And so you see the light make this sort of bouncy movement. And that means it's actually traveled farther than the person on the ground who thinks that the mirrors are just sort of, the light is making just a straight up and down line from mirror to mirror. That question that you asked is what completely revolutionized physics. Everything fell apart when people said, how do you even measure time? What does it mean to make a clock? What are we measuring? I still don't understand what we're measuring.
Oh, Lord. Yeah.
I get it. I mean,
I don't know if I have an answer for you. I don't think anybody does. But here's the deal. So the clock in Einstein's experiment, so the clock has, two mirrors and there's light bouncing between it. And then and that's the distance that it travels in one tick.
Right.
But now you put that clock on a spaceship, and the spaceship's going really fast. And as it goes by, you see that clock, as it streams by you really fast, you see the light make this motion. And this line is actually longer than that line. This line, if you measure it, that's actually a longer line that I drew than the original one between just the two mirrors, because now it's at an angle. And this is what made Einstein say, time has to change. If anything moves, the tick of a clock changes. However you measure time, whatever time is, whether you measure it with a bouncing clock or whether you measure it with a vibrating atom like we do in the Bureau of Standards, or whether you measure it with a spring that's slowly unwinding in a wristwatch, anything you can do to measure one moment to the next changes when motion is involved. There's no way to get around it. It's not just the measurement. It's time itself is changing. Any way we have to measure this thing we call time. And I have to tell you, Joe, I don't think we have an answer to what time is. What are we measuring? I think right there, I think you're asking for the next revolution in physics that we don't have yet. I really mean that.
So when we're measuring time currently, like when I look down at my watch, I'm measuring time in this particular space. like where I am, what altitude I'm at,
Right.
how fast I'm moving, and the watch just does a reasonable job of calculating all that.
And that's you. I mean, that's what you see here, sitting still with your watch, looking at it.
Right.
If someone's flying by at close to the speed of light, they won't see you measure time the same way. Yeah.
But you said something else too that freaked me out. That if you traveled at the speed of light, the problem would be you would have infinite mass.
Well, anything with mass. Yeah. That's the thing.
So if a person was
Yeah.
in a spaceship and it traveled the speed of light, that spaceship would have infinite mass.
It's basically it's what makes accelerating up to the speed of light impossible. That anything with mass can't travel at the speed of light. I mean, the equations blow up. But what does infinite mass mean? Do you have more mass than the whole universe? What the hell is that? As you approach the speed of light, if you have mass, it takes more and more energy to accelerate you even just a little bit more. So you never get to the speed of light. You know, you're going 99.9% the speed of light. Okay, I want to go a little faster. It takes more and more energy each little tiny step you make. It's basically you never get to the speed of light. It takes an infinite amount of energy. So, you know, when it comes to things like interstellar travel, I don't think we're ever going to take a spaceship and accelerate it to the speed of light. I mean, we might get very close. There are particles in space that do have mass, like neutrinos, tiny little bits of mass. They travel very close to the speed of light, but they don't travel at the speed of light. But to me, you know, I think that the idea of traveling interstellar distances or even intergalactic distances, you know, the thing that starts to really get me is the question of this what is space and what is time at all, quantum entanglement.
Right. Glad you brought that up.
Oh, yeah. I'm going to say I hope your listeners. I don't want to get. I want people to come along with us.
Oh, they're coming along. Don't
Yeah,
worry.
I don't want to say things that sound so stupid. They're like, you know, why are they saying this? So please stop me if we need some more background.
This does not sound stupid in
Okay,
any way, shape,
okay.
or form. But the idea of quantum entanglement, we should explain that to people.
Yeah.
And what it essentially means is that things are entangled, they're connected at regardless of the distance.
Yes.
And it could be an immeasurable amount of distance, like
Any distance.
Like, yeah, literally the beginning of the universe distance, like 13.8 billion light years away distance. You're entangled with that.
It's amazing because once again, let's go back to the idea that this is a real experimental fact, right? I mean, a lot of times this crazy stuff that, you know, scientists will say this stuff and people hear it, you know, for the first time and they say, well, that sounds like idiotic. That sounds stupid. Where did they get that from? And the idea that time changes is now, it's one of the most commonly proven facts every day. Like I said, we need it to calibrate the GPS satellites. It's easy to measure. Quantum entanglement was something that even Albert Einstein 100 years ago, he understood that quantum mechanics was pointing that way, but he really didn't like it. He called it spooky action at a distance. He hated it because he realized that quantum mechanics had this implication that if things could somehow be connected quantum mechanically, you could take them any distance away from each other, and they would somehow be able to respond to each other instantaneously with no time difference. And you know, he didn't think that would ever actually happen. And then back in the mid 1990s, we started to do experiments with atoms, and we found out that it was real. That it can start off pretty simply. You have two atoms that are in an orbit around, and you know, so an atom has a nucleus of protons and electrons in the middle. Oh, sorry. An atom has a nucleus of protons and neutrons. The electrons are flying around in orbits around the atom. Two electrons can be in the same orbit only if they're spinning in different directions. They have an angular momentum. It's called spin. And the only way these two electrons can fit in that orbit together is if they're spinning, one is spinning in an upward direction, one's, say, spinning in a downward direction. Hate the broken finger. So if you take these electrons out of the atom, and you can do that, you know that they're in different spins because they had to be in that orbit together. So now you separate them. You can separate them by any distance you want. Can separate them by centimeters in a laboratory. The Chinese have done this up to the space station that they run and back. You could conceivably do it to another galaxy. If you take those electrons and you separate them, you know that they were spinning in opposite directions. So if you take an electric field and you change the spin of one, the other one immediately changes in response.
Regardless of the distance.
Regardless of the distance. And we know this to be true. We've done this. And the amazing thing is the universe is saying these two things are the same quantum mechanical system. They're basically the same object. They're connected to each other. They're entangled together. And it doesn't matter. Space and time don't matter. You separate them in space any distance you want. How does that work? The universe says the space and time between them doesn't matter. They're the same system. To me, that's the real intriguing thing about, could a civilization learn how to harness that? You're not really even having to worry about traveling from one part to another. Did you watch the three-body problem show?
Yes.
So you have these things called sophons, right? And sophons are entangled to this alien civilization. And they can respond instantaneously because they're entangled. Yes, I mean that's fantastic science. And as far as I can tell, that could be theoretically possible. Yeah.
Well, that's what's bonkers, is that we are made out of all this stuff that's entangled.
What's it entangled to? Is it entangled to stuff inside a black hole right now? Is it entangled to stuff that is on the other side of the universe from us? If the Big Bang had all of this stuff in a small volume at once, are we entangled to everything in some way? Seriously. I mean, is a part of me quantum mechanically right now in the Andromeda galaxy? Yeah, actually. That would be the implication. I mean, talk about, I don't think we understand yet what reality is. I really don't. What does it mean? Are we all somehow the same particle, entangled to each other? Are we connected to everything all at once? I mean, that could be where physics is taking us now.
That's bananas. It's very difficult to think about when you think you're a person in Austin, my feet are on the ground.
Yeah.
Here I am touching this desk. I'm going to get in my car later and go get something to eat.
No kidding. You got to feed the cat, right?
Yeah, but that's not really what's going on. It's way more complex, way bigger. And you were speculating that could be how some super advanced, intelligent life form travels.
It's always been more compelling to me than the idea of taking a spaceship and traveling somewhere.
This seems super crude.
Yeah.
That seems like the idea of making a horse fly.
Yeah. Yeah. We talked about that movie Interstellar because there were a lot of good teaching moments in that movie for a physicist. The idea that time really does slow down close to a black hole. And again, we observe this. When we observe things orbiting close to a black hole, you can tell that happens. And the idea that this advanced civilization that we never actually see in the movie somehow communicates through basically space and time itself, through gravity. That's how Matthew McConaughey is able to even go back, in time and space to help his daughter solve, gravity and all that. I was like, I wonder if that's really more what it'd be like. Advanced civilizations. I mean, you got to think, right? I mean, you look around the Earth and there are, things like grasshoppers and hamsters that are fantastic, incredibly complex beings. But I mean, you try to teach them quantum mechanics or ask them to, crochet a blanket or whatever. They don't have the capacity. And you've got to think that there's the similar jump where, I mean, we don't even know the right questions to ask that sort of a civilization. I mean, can they see the universe as a whole thing? Do they know that they're connected to everything? And can they somehow use that to travel? Maybe. Yeah.
Maybe, and if you just extrapolate, if you just think about where we've gone from primitive man to what we're currently experiencing, and you take that thousands of years, millions of years, whatever it is, you keep going. And as long as civilization gets rid of war and figures out a way to not die of disease and natural disaster, you could potentially continue this process of technological innovation for millions of years, and you would imagine that it would go exponentially greater and greater in its ability to do things.
Yeah.
And its ability to not even things that we can imagine. Like, we have a crude understanding, amazing understanding of the universe, but crude in comparison to what's potentially out there. What we could potentially be observing in a physical way every planet on every star one day. But we can't even think of that as being a possibility now. But what we're doing right now is insane to people that lived in the 1400s.
Yeah.
If you showed someone from the 1400s a nuclear power plant, they'd be like, what the fuck are you guys doing? Like, what is this? If you showed them a nuclear detonator, if you showed them FaceTime on a phone, they'd be like, this is insanity.
I just got on a little metal tube and came here from Milwaukee, and I'll fly back tonight. Yeah,
Nuts.
Yeah, absolutely.
And we're just accustomed to it. It becomes normal. And it would become normal as technology increased further and further and further. And this idea that the entire universe would be accessible is just bananas.
Have you ever wondered if maybe the real follow-on to humanity someday will be some form of AI?
I think so.
I mean, yeah. I do wonder if the human brain is just kind of limited. I mean, if you say there are multiple dimensions and time is something that changes. I mean, I just said that, scientists are no better than anybody else at comprehending a big number or a big amount of space. We just kind of get used to it. Will we have a creature someday that we've created, an AI, that then all of a sudden can comprehend these things? Is that really the real evolutionary path of humanity?
Yeah, I think so. I think it's just a completely different kind of life, and that we're thinking of it as artificial. I don't think it's artificial at all. I think it's a life. It's just a different kind of life that we're creating.
It's an earthling. I mean, seriously, it's our children. We created this.
Yeah. I always describe ourselves as like we're an electronic caterpillar, and we're making a cocoon. We don't even know why we're doing it because it's just what we do. I mean, the thing about human beings is we've always been completely fascinated with innovation. I've always said that if you looked at us objectively, what does this species do? Oh, they make better things. They keep making better things. They're never satisfied with the things. Bees made the beehive and like, I think we got it, boys. This is it. We're not satisfied at all. And so if you just kept going with that, like, where does it go? Well, it has to go to life. It has to go to some sort of a human-created new kind of life form that exists out of the components of the earth, but instead of being born out of evolution and out of natural mutation and natural selection, it's a random mutation. It's made out of us. Mm-hmm. We made it, and it'll probably make better versions of it, and that would be the new life. And that's how you get over all the biological hurdles that we have. You think about like the things that trouble us, war and crime and violence and all these different things that are a real problem with the human race. Well, that all goes away when you stop being human. And if we really are entangled with everything, that will be us. It'll just be us in a completely different realm.
Yeah. I do like this idea that what we call AIs now isn't something separate. I mean, they are our children. It is an earthling. It is something we've created. The question I've often wondered is, sometimes I think sometimes we lack imagination about what might be possible. I've always enjoyed science fiction where the AIs also learn about love or about the arts or about creativity. I mean, whether you want to go with like the new Battlestar Galactica or whether you want to go with a pretty profound experience I had with a friend of mine who's an author who has cochlear implants. And, he realizes that he doesn't hear like a human. The cochlear implants don't replicate perfectly what it means to hear the way our ears do. They bypass our ears. They wire directly into his brain and stimulate the experience of sound. And so he's hearing, in his words, like a cyborg. This is Michael Korist, a wonderful man that did some essays about this. And he talked about how much emotional response he has to music now, something he could never experience, how being a cyborg, quote unquote, and experiencing something in a non-human way has added joy and depth and passion. Are we so sure that technology makes us more and more, kind of 1950s robot-like? Or could it take us into new experiences of being connected with each other, new ways of loving each other, new ways of understanding things? I mean, does it have to be all bad, this?
Well, all of our differences fall apart if we realize we're all one thing.
Yeah.
If we realize we're all one thing, then all of our monopoly of resources, all that stuff goes away.
Yeah.
If we realize we're all one thing. I mean, part of the problem with human beings is we're very selfish. And the reason why we're very selfish is because that's how you had to survive.
Sure.
If you wanted to survive and you wanted your genes to be passed on to the next generation, you had to be selfish because other people were being selfish too, and that's the game that humans were playing. If we get to a point of universal telepathy, like universal telepathy with a universal language where all human beings are sharing thoughts. There are no secrets. We are all one thing. Everyone's terrified of that. People love secrets. I don't want people listening to my phone. I don't want people. Well, I don't either. Because it would be people doing that, and those people have their own ulterior motives, and it's gross that they would have control. They know your emails. But what if there's no secrets? It's not possible because our understanding of each other is now complete. Mm-hmm. It's like we read each other's minds in a sense, but it's much more complex than that, and much more in depth. Like you feel what that person feels. You are that person, and we're all one thing. That could be possible through technology, and this is where I have hope. Where a lot of people are like very fatalist with AI, and they look at it in this dystopian sense that these oligarchs, these technology oligarchs, are going to be controlling us through AI, and they're going to have access to it and power. I don't know if anybody's going to control it, and I have a feeling it's going to be kind of like the internet in a way where I don't think they really thought what the internet was going to be. I think they had this understanding of being able to exchange information through universities, and I think it got to a point where if they knew what the internet would be today and how little control they would have over the population and narratives, and I think they probably would have shut it down a long time ago. I have a feeling that's going to be the same way with AI, and especially AI as it integrates with us, which I think is the only way that the human species really truly survives. Otherwise, we're just this archaic biological entity living in this new world of this ultra superior life form. But if we integrate with that thing through wearables, implants, engineering, if we figure out a way, and this is going to sound terrible to anybody who loves being a person, but all the flaws of being a primate. There's a lot of these biological reward systems that are built into us that are really problematic for progress. I mean, the reason why are we at war right now? Well, because there's people with certain ideologies, and there's resources, and there's people that are making money from their military contractors, and there's politicians that are beholden to certain interests. And then what are we doing? We're doing the same stupid shit that we've been doing for thousands and thousands of years. Well, how do we get past that? We get past that by stop being people.
I think you may be right. I mean, again, that future it's frightening in some ways, but I'm more interested in the imagination. I mean, instead of just the dystopia, what could this mean?
Right.
I mean, how much more? Like we said, I mean, when we were little tribal groups, the little wars we had, the skirmishes, didn't really hurt the planet as a whole. I mean, now there's so many people, and we're still having these little tribal skirmishes, and now we're in danger of massive destruction. I mean, we can't just keep going this way. I mean, it's not survivable.
It's not.
So, I mean, could AI help us, tap into some kind of group consciousness? I mean, when we're talking about Einstein's idea that the universe may all be this one big thing, and this is pure metaphysics, pure conjecture. But even when I was a little kid and I heard that, I wondered, well, if all time and space happens at once, is there need for more than one consciousness? Even are we all just looking out of one consciousness looking out of everybody's eyes simultaneously, and not just humans but everything in the universe? It's a spectacular idea that if there is a moment, if the universe is just one big thing, we are part now, even now, of beings we have no names for, super advanced beings that have figured all of this out and can span the universe with their consciousness. That's part of the eyes too. I mean, that's another part of this consciousness that we're part of right now. If there's one instant, it reminds me of some of the tenets of Buddhism. There might be these perfectly enlightened beings, bodhisattvas, and we are past lives of them. We're all existing at once. It's a fantastically beautiful idea.
It is a beautiful idea. And our survival instincts are attuned to maintaining what we are. There's this thing, well, I don't want to lose being a person. But I guarantee you, if you went to an Australopithecus and you could somehow communicate to them, listen, you're going to change, and you're going to be this thing that gets sick 7 times a year, and maybe you're obese, and maybe you have a problem with cigarettes, and maybe you drink too much and you like to gamble, and you're going to fuck your life up here and there, but you're going to have a cell phone, and you're going to live in a city, and you're going to be breathing brake dust every day, and your doctor's going to give you a bunch of stuff you don't really need because he's trying to make money. The Australopithecus are probably like, fuck that. I know what I'm doing here.
Sounds much better.
Yeah, I know where the food is. Like, get out of here. I don't want any part of that. And I think that's just part of survival instincts. Survival instincts don't want you to radically change into something completely different with its own new set of problems. You want to stay. You want to maintain. Country boy can survive. Keep me in the woods. You know what I mean? Like people have this like natural inclination to keep things simple because they understand them. But I think that's not possible anymore. And I think we're going to just have to let it go. Just let that idea go and relax and accept whatever this new thing is. And I think we're very, very fortunate to be born at this time while we're experiencing it. Regardless of the outcome, this is a very unique time. Like one of the weirdest times, I think, objectively in human history. And we're very fortunate to be experiencing it.
I mean, you and I are roughly the same age. And, I think that, for me, having this, what they now kind of, call the feral childhood, right, where I was unplugged. And there were vast stretches of time, even as a small child, where I was on my own, in the neighborhood and stuff. And I loved it. I mean, I remember going to, a YMCA camp when I was 11 years old. And, everybody had to show up at breakfast, and then there was an activity time, and everybody had to show up at lunch. But what you did between that time, you were on your own. I mean, as an 11-year-old kid, in the woods, there were activities. You could do some archery. There was a riflery. There was craft shop. There was swimming. And you had to check in at certain times. But sometimes I just went and sat in the woods. 11 years old. I mean, can you imagine?
I had a similar experience in the Boy Scouts.
Yeah. And, the thing was, so you and I had this experience of living unplugged and sort of the idea of a quiet mind and imagination. But we also saw this tremendous change and this connectivity, which I love. I mean, I also love having the internet and my cell phones and all of that. But this is a real change in human civilization that we went through personally. And I agree with you. I feel a tremendous sense of gratitude for both ends of my life.
Right. We could have been born in the 1500s, where the 1500s to the 1600s, not that much changed. I mean,
for a lot of people, yeah.
Sure.
Yeah.
I mean, politically things changed. Leaders got overthrown. But as far as like the way you interfaced with the world, pretty much the same way. You wrote stuff down with feathers.
Yeah. And gratitude. And like you said, I mean, maybe instead of all of the dystopia and all the worry and all the panic right now, going forward with gratitude.
Yeah. Well, I think the unknown gives people a tremendous amount of anxiety.
Sure.
For a good reason. I mean, the unknown could potentially be dangerous and scary and terrifying or awesome. And you really don't know. And so you're like, what is it going to be? And there's all these college kids that are really freaking out because they're went into debt. They're getting these college degrees. They're leaving with this burden, this financial burden that they can never get rid of. And on top of that, they have a degree that might not be worth anything because AI might completely eradicate their field. That's a real concern. And so I think kids today that are graduating from college and graduating from high school, they probably have the most amount of anxiety about the future. That, and then there's people that, they haven't saved any money up. They don't even know if money's going to be valuable in the future. Like, what does it even mean? Are we going to abandon all money? Like, what is it going to mean when AI completely controls all of the resources, all of the government, all of everything, all transportation? And you don't have to do your job anymore. You just get some funds from the government where you can buy food. Like this is what people are talking about. Like this is a potential, 100 years from now future.
Very seriously so. Yes, absolutely.
Yeah. Which is terrifying to people that are thinking, hey, I want to do what my dad did and what my mom did, and I want to go out there in the world and I want to find something that I'm passionate about and make it a career. And like maybe that's not possible. That to kids right now, I think is really freaking them out because the adults, the people like us that are supposed to be the ones that say, well, let me tell you how it all works. You're going to be fine. This is what you have to do. And if you do that and you just cross your I's and dot your T's, you're going to be okay, Bob. But maybe you're not going to be okay. Like maybe we don't know shit because that's the reality. The reality is you and I, the adults, have no idea what this world's going to look like in 50 years. And these poor kids they have no one to turn to. There's no one that can explain what this, and so they're entering out into the world, having to take care of themselves for the very first time with this real possibility that there might not be any jobs.
Mm-hmm. On the flip side of that, are you in fact describing the Star Trek universe?
Right.
A time where people do not work everybody has, anything they need as far as, apparently survivability, food, whatever. And now you have a chance to say, am I going to be a writer or an explorer or an artist or a captain or a musician?
Yes.
Is there something in that might be hugely liberating?
100%. And I've talked about this as well, that this idea that you have to toil and you have to be a hunter-gatherer or, you have to do this in order to find meaning in life is kind of crazy because we can find meaning a lot of ways. There's very wealthy people that never have to work that have tremendous meaning in their life because they're doing things all the time without thinking about work at all. They're not thinking about it as work. Whatever hobbies they're pursuing or interests or education they're pursuing, they're doing it just out of pure interest and fascination and love and passion. And that could be all of us. But there's going to be a tremendous transition period where people are going to have to rethink what it means to be a human being in society. And that's what's weird because our entire society is structured out of getting up in the morning, putting in the work, working towards a future. You got a 401k, you got investments, you got this, you got that, you got a mortgage. And this is how we've structured our entire existence and what meaning we gather from life. It's based on that. We're going to have to figure out a way to realize and to rethink this. And it's going to be very difficult for people that are like 40 and 50 that are just completely set in their ways. And now their ways change. And I don't know how many of them are going to be able to make that switch and what could be done to assist them in that. What can be done. And maybe that comes with whatever this technological interface is. Maybe that comes with when we become what's essentially a cyborg. That you get a much greater understanding of what it means to exist, and that this idea that you exist only because of the insurance company you work for is kind of ridiculous, and we abandon that. I mean, in the way that now when you open up your phone and you use Perplexity, you have access to something that's as smart as every human being on Earth in every field. You can ask it about anything, and it'll give you the state of the art. And whatever the science is, whatever the understanding of history, whatever mathematics, tax law, whatever it is, it can give it to you on your phone instantaneously. And we've just sort of accepted that. This is our new thing. And I think this is like a baby step into what this technology could potentially, if you're looking at things with a glass half full, it could potentially change the way we look at everything. The way we look at ourselves, the way we look at what it means to be a person, and what we find meaning out of. And this, because that's the problem. The problem is meaning and the feeling like you matter, feeling like you're important. And I think part of that is because we're also isolated from each other. But that might go away entirely if the boundaries between all thought and consciousness, if we realize like, oh, consciousness is just a thing that we're all enveloped in, and what our brain is just a antenna. It's like tuning into consciousness. And depending on how good your antenna is, you're going to be a little bit better about how you interface with the world and whatever thing you desire and whatever thing you decide to put your energy and attention to. Maybe you'll be better at it than another person because you have a better antenna. But we might understand that like we are really, truly all one thing. So all our fears about, finding your place in the world, that might be nonsense.
I really like that idea. I like the idea of search for meaning. And I agree with you. I think that as like you said, as Australopithecus, as people that used to exist in these little tribal groups and families, the modern isolated life, I mean, it's something that I struggle with a lot. I'm always wondering, where is my family? Where are my friends?
Right.
I've had to do a lot of sort of interior work about, I'm just going to bring along my own family inside somehow. I mean, I have to provide this all for myself. The idea of being less alone, being less isolated, that's one thing that I wanted from the internet. It started out on Facebook. I could keep up with my friends. I saw what they were doing. They were posting pictures of their life. It was less isolating. And then now it's evolved to I can't even find them on Facebook anymore. It's all all the ads and everything like that. But I mean, for me, I mean, you talk about meaning and you talk about solving isolation. Tell me more about that. I mean, how has your sense of meaning in your life evolved? How has it changed over your life? How do you find meaning?
I find meaning in well, there's a bunch of things, right? First of all, it's the people that are in your life. This is a giant factor because without people that you love and people that you enjoy spending time with, life loses all of its value. If you're an insanely wealthy, insanely successful person who has no friends, who lives alone, you're living in hell. And if you are a poor person that has amazing friends and you're just getting by, you are a happier person. But I guarantee that poor person would switch places with that rich person in a heartbeat because we're programmed to think that success is numbers, that success is what you can accumulate as far as like objects and desired material possessions, but it's not. It's like true success is happiness and the amount of joy that you get out of life and the amount of satisfaction you get in what you do. So I think for everybody that answer is a different answer because for some people it's going to be music. For some people it's going to be they're going to write. There's going to be a thing that you enjoy putting yourself into that you feel satisfaction and you feel meaning with on top of friends and family. So friends and family, I think, is foremost. But then they can get in the way, too, if they don't have their shit together. So, like, they have to have a thing that they're enjoying as well. They have to have a thing that's helping them grow as an individual. And there's a thing from martial arts. My instructor told me that when I was very young that I never forgot, that was martial arts is a vehicle for developing your human potential. And that if you find things that test you and you find things that are complex and these puzzles that you have to solve, the more you do that, the more you get of an understanding of who you are and what you can do and what you can do out there in the world. And the more you do it, the more you can do other things. And I think that's where I find meaning. I find meaning in doing things and enjoying time with my family, enjoying time with my friends, having joy and fun and laughter, and then also difficult pursuits. I like things that are complex, the things that are hard to solve. I like things that are hard to do, where I really have to force myself to do it, and then I feel satisfaction afterwards, and I understand my ability to force myself to do things. And in doing that, I find meaning. And I'm a relatively happy person. I think I'm very happy in terms of like the average person. And I think that's why. But if someone just took that all away, if all that's gone, would you still have happiness? Like, what is happiness, right? What is meaning? And is it entirely connected to your job? That seems kind of crazy because a job is just a constructed thing that it would, 500 years ago didn't even exist. So do we have to have meaning? Are we these complex problem-solving biological organisms that have this thirst for innovation and to constantly make things better? Are we tricking ourselves with jobs to be happy? Are we filling the need of whatever? Like when a cat chases a ball, what is it doing? Well, it thinks it's killing something. That's its design. This is its biological need. You throw a ball past a cat, it goes after it because it's got this biological need to chase things that are running away from it so it could kill it and eat. And I think we're kind of doing a similar thing with our hunter-gatherer tribal organism that we're still trapped in, that we're tricking it. We're tricking it with complex problems, and we're tricking it with community. We're tricking it with all these different things that keep it happy.
I agree with you. Yeah, I think that's a wonderful answer. I mean, there's something about the happy poor person, isolated rich person thing that I agree with. At the same time, seeing what grinding poverty does to people's minds and breaking them down with exhaustion and demoralization. There's obviously some kind of a sweet spot for there. I mean, I've had to work quite hard in different parts of my life, and I was just very aware of the soul grinding, not having enough, and wondering where your next meal is coming from, and I have it nowhere near as bad as some. But the thing that was absolutely for me unbelievable about working for NASA was the idea of solving complex problems with people you trusted and people that you thought you really had your back. And no organization is perfect. But, the idea that it's not a zero-sum game, right? I mean, you want the whole team to succeed. I mean, even if there are missions you think should have been lower priority, or maybe we should spend more money on this and less money on that, at the end of the day, you want whatever's going on to be fantastic, and you want it to succeed, and you want all the people around you to succeed. And the idea that, again, I mean, this isn't hunter-gathering. I mean, we're solving problems. We're saying, can you take a picture of the black part of a black hole? Can you actually see the light area, the event horizon getting sucked in? I'm talking about the Event Horizon Telescope, not a NASA mission. But, there were times in my life, like when I first saw that picture come together, and I didn't think they'd be able to do that. I don't think people really understand what happened there. They were doing something right on the fuzzy edge of physics being possible. You need to catch the same front of a wavelength of light, right? So light's coming by, it's a wave, it travels at the speed of light. The wavelength of light is tiny. Let's say for a minute, they were dealing with microwaves, so let's say like a millionth of a meter. So something that's a meter divided by a million is traveling past you at the speed of light. And the Earth is round, and the Earth is moving, and they had these 8 observatories all around the planet. And they had to catch that same wavefront, the same one. If it was one wavefront later, one millionth of a meter later, traveling at the speed of light, they wouldn't have gotten the image. They needed to catch the same wavelength, the same photon, the same wave of light had to be caught in all of those telescopes at once. One was at the South Pole, somewhere in the United States, somewhere in Chile. They were all over the planet. And if you caught the same frickin' wave of light.
Here it is.
There you go.
Wow.
They managed to make a telescope that's actually as big as the Earth. And they were able to take a picture of the dark parts of a black hole. Now that's something called the shadow of the event horizon. It's basically the event horizon where time and space stop. We don't even know if there really is an interior to a black hole. All the equations blow up. Time and space don't exist in there. And light, nothing can escape that darkness. The black spot you're seeing there is a little bigger than the event horizon itself. It's called the shadow of the event horizon because time and space are bent around the black hole. And so some of the light that actually gets sucked in is the light that would have gone around the black hole. It gets sucked into the back end of the black hole. Literally space and time curve around the black hole. And so that dark part is actually a little bigger than the event horizon. It's called the shadow of the event horizon. And they said they were going to go take a picture of it. And I was like, you have to catch the same wavefront of light in all of these telescopes. I mean, that's going to depend on the height of the mountain, how fast that part of the Earth is moving. They did it. They fucking did it. And they didn't do it just once, right? And, and now we can take a picture of an area right in front of your eyes where space and time doesn't exist. I mean, to a lesser extent, one of the NASA missions that I thought was just spectacular was a small, inexpensive mission called NICER. You're like, who's the nicer person? NICER, N-I-C-E-R. It's the Neutron Star Interior Composition Explorer. And a neutron star, you probably know about these, but when a star dies and the nuclear reactions inside a star cease, all of that gravity of this massive object comes crushing in. And it'll create an object sometimes called a neutron star. They're about 20 miles across, but they have about twice the mass of the sun. And we study many of these at NASA. They're all over the place. They're real. They're something you can take an image of. You can take a picture of. And these neutron stars have physics that we don't understand. You take 2 times the mass of the sun, you crush it into 20 miles. We know that we can't describe the interior of that thing yet. We don't have the physics that matches that type of density. And this crazy little contraption. I mean, it's about the size of a washing machine. It was built in a lab just on the floor that I used to work at NASA. It's cheap, easy to make. I shouldn't say easy, but I mean, it's actually able to create maps of what the surface of these objects are like. They're 20 miles across. They're thousands of light years away. And you can actually create a map of what the temperature is like. And one of the things we see on these maps is the distortion where space and time curves around these objects. They rotate very fast, and there are hot spots we see coming in and off the neutron star. But then as the hot spot goes behind the star, the light bends up and over, and we can actually still see the hot spot because space and time are bending around these objects. You can see that. That's not a mathematical simulation. That's not a theory. You can see space and time bending around these objects. You can see space and time bending into that event horizon. It's absolutely crazy what we've been able to do. And whether it's a huge project like the Event Horizon Telescope, where I would have bet that they would not have been able to make that measurement, and they did. There were so many hard drives of data. One of the telescopes was at the South Pole. And you wanted the telescopes to be as far apart on the Earth as possible, because then you could basically make a giant telescope the size of the separation of these telescopes. And there wasn't there's pretty good email links down to the South Pole, but the email link wasn't fast enough for all of this data. They sent back literally, there was a ton of hard drives to actually, they had to play them all at the same time and make sure they caught the same photon. If they had caught, seriously, one photon following behind the other, the image wouldn't have worked. They had to catch that same photon. Humans are incredible.
Some of us.
Oh, hey.
Some of them, I should say.
Maybe pretty much all of us in different ways.
Yes.
I
Unrealized potential.
No, I got to go back to this. One of my good, I have 3 friends now who've won the Nobel Prize, which is always like, what the hell am I doing?
That's awesome.
But
good friend group.
Oh, yeah.
But you have good group chats.
Well, see, the funny thing is we certainly don't all get together and talk theoretical physics. That's not really what we do. But I was seated next to one of them at a meal one time, and somebody came by and said, "Oh, look at all the brain power here." And I actually, I try to be kind of nice about it, but I said, there's a single mother working 3 jobs part-time, who's waiting tables over there. And the mental capacity and the strength of that person is something that, don't look at us. Go praise that person.
Well, that's brain power too. It's just a different thing.
It's survival. It's trying to keep your life and soul together.
Yeah.
The privilege of being able to work at NASA and to be able to work with a team like that and do things you think are impossible. That was kind of a part of my life you could stick a pin in and say that meant something. That gave me some meaning. That gave me joy. And as you said, it's not so much being a hunter-gatherer. It's can we ask a question that we think is impossible, and can we just go and do it?
Yeah, the ultimate expression of human curiosity. When you say that we don't have the physics, when you're trying to understand what's happening in a neutron star, what do you mean?
So you can measure how big these things are, and you can measure how massive they are. And so then you can do a calculation as to what the density inside would be. And, probably the interior core is denser than the outer regions, but if you had a teaspoon of this material, it would have about as much mass as Mount Everest. And the reason they're called neutron stars is that the gravity is so intense on these things. I hate sort of a simple view of atoms as little balls going around each other, because they're not. They're waves of energy. But the gravity actually crushes the electrons into the nucleus. They combine with protons to become neutrons. So they're mainly little balls of neutrons. But we do, there you go. You see the big question mark there at the core. So here's the problem. You run our basic laws of physics, our understanding of how particles work. And you get to the density of a neutron core, and the equations don't work. They're not making the right predictions. We can tell that there's actually a really great NASA video I would suggest you watch. It's called the interior of a neutron star. Well, I can help you find it, but it basically says that the models we have about how matter works at that sort of density, none of them give the right predictions for the size of the neutron star.
Why is that?
We don't have the right physics for it yet. So we run our physics and we say if you have this much volume and this much mass, what should that interior be like? And none of our current models of how matter works gives us the right observations, gives us the right size.
So what are we missing?
Well, for one thing, what you're probably looking at inside a neutron star is some type of interaction of quarks, the actual sort of building blocks of neutrons and protons, the particles that make up protons and neutrons.
Ooh, that's cool.
Yeah, you got it. You're amazing. I have to say, I'm seriously impressed by this person's ability.
The best.
Yeah. So, this is a video that it was done by NASA, testing matter's limits. It's a 4-minute video, and while I don't think it's an absolutely perfect video, I think it's fantastic. And so you see this is supposed to represent the electrons being pulled into the nucleus and making neutrons. And then at the very heart of these things, we're in a state of matter that we have no description for yet. We can't tell you how it behaves. We've never created it in a lab. We don't know how this type of matter acts. It's a new state of matter. We don't know what it's like.
Wow.
And it's made when one of these giant stars explodes. The core of the star becomes compressed, and then this will take you through us trying to figure out whether you have particles as discrete particles, as neutrons and protons, or whether there's some type of quark soup inside. But pretty much every model so far doesn't match what we actually measure from these things. We cannot describe them yet. We need better physics.
Are there any other structures that are similar in our lack of understanding of them in the universe?
You got two big ones right in front of you: neutron stars and black holes. Right. So I mean these black holes as well. What is inside a black hole? Is there an inside if space and time don't really exist? And then much more easy to see are these neutron stars. The people who study neutron stars at NASA, they have this wonderful expression. They're like, with a black hole, you can't see anything. It collapses into an event horizon. Nothing's coming out. With a neutron star, you got the frickin' thing right there in front of you. You can actually observe something. And so, they figured that neutron stars are much more exciting than black holes because you can actually do experiments, take a picture, build a telescope. And But this experiment was an inexpensive, small observatory that's up on the International Space Station, and I mean, they're doing incredible work about the nature of physics and testing where our limits are. It's unbelievable what you can do with even a relatively inexpensive mission.
When you look at the size of some black holes, we were talking the other day about the largest black hole where the event horizon goes past Pluto.
Yeah.
If it was the size of our solar system.
Absolutely.
That's almost impossible to even think about, that there's a black hole that's bigger than our solar system. And how did it get that big?
Yeah.
How much time does it take for it to gather up that much matter to get that big?
Well, you were talking about these little red dots that the Webb telescope is seeing. So, I mean, what you've just done is put your finger on, I think, one of the most fascinating unanswered questions in astronomy right now. That every major galaxy has a big black hole in the center. The one in the middle of our galaxy is about 4 million times the mass of the sun. And physically, it's not that big. It's about, let's say, around about the orbit of, say, the inner solar system Mercury, so kind of around there. But then the bigger ones we know in other galaxies can get up to hundreds, let's say, tens of billions of times the mass of the sun. And those, the event horizon's about the size of the orbit of Pluto. The question is, how do you gather 10 billion times the mass of a star together in the beginning? Black holes, the only thing we know that forms big black holes like that, so a star collapses, a star dies, and this tremendous crush of gravity as the star collapses creates this bottomless pit of gravity called a black hole. So how do you get that many stars to die? In the early universe, how many stars, how many generations of stars had to burn through to actually get that to happen? And there was nothing that we could figure out. I mean, how do you make that big of a black hole? So these little red dots that we're seeing with Webb, and when we don't know exactly what these are, but right now the observations are pushing us in a very interesting direction. They're about 1 million times the mass of the sun. And at first we thought, okay, well, are these whole galaxies? And that was the controversy you alluded to, that how could there be galaxies that far back in time? We're looking back to a time about 400 million years after the Big Bang. We're looking so far away. The light took that long to travel to us. So we saw these sort of bright objects. At first we thought they were galaxies, and that was like, whoa, how'd they get there so fast? But then we took a better look at them, and they don't actually shine in the same light a galaxy would. They appear to have the signature of something inside, some of them rotating very fast, very fast. And what we're wondering is if the first generation of stars, the very first stars that existed, were nothing at all like the stars we have today. The universe was denser. There was probably more of this stuff called dark matter that had gravity pulling everything together. So maybe at that time, the universe there were cores of huge amounts of gas that collapsed together. Instead of forming a star, the core basically collapsed into a black hole immediately. And it started pulling in material, and all this sort of hot stuff formed what they call a pseudo-star. There's all this atmosphere of hot gas being heated up by the black hole in the middle. As the gas spirals in towards the black hole, it gets hotter and hotter. So instead of a nuclear fusion core of a star, you have a black hole heating everything up on the inside, accumulating all this mass. And are we looking at, for the first time, the seeds of these giant black holes? That instead of there being, the first thing was stars, the way we think of stars, was the first thing huge amounts of gas and dust collapsing into black holes and heating up sort of a pseudo star around it, millions of times the mass of the sun. And then in a dense area like the heart of a galaxy, these things then start to combine. Over time, gravity pulls them together and you build bigger and bigger black holes. So once again, we don't know yet that these are that these objects are. But at the moment, it's one of the best explanations we have, and it fits the data quite well. So we will keep observing these things. We will keep finding new ones. One of the big questions has been, why don't they give off more X-rays? Because if there's matter streaming down a black hole, it should give off very high radiation like X-rays. And then just in the last couple of months, there's some observations coming out where we're finding some of these are indeed X-ray sources. So we may have found the answer to where you get these big black holes. Wow. And that was one of the big hopes for the James Webb Space Telescope, that it would help us answer the question of where do you get these giant black holes in the cores of galaxies? Where do they come from? There shouldn't have been enough time for that many stars to make them.
I watched a documentary on black holes once where they were talking about that in the center of every galaxy, there's a supermassive black hole that's 1/2 of 1% of the mass of the entire galaxy.
It seems to be correlated. Yeah, the bigger the galaxy, the bigger the black hole. Yeah,
which is nuts. And what they were theorizing was that if you went through that black hole, you could potentially be in a completely different universe, filled with galaxies, all that have black holes inside of them. Through that, another universe, that you would have an infinite number of universes that exist, and there's these like black holes, and if you can go through them, all of them, it broke my brain because I'm just sitting there, I'm thinking, like, wait a minute, how many billions of galaxies are there?
Yeah.
Like what? And each one of them has a black hole in the center of it?
Mm-hmm. Yeah. Well, and I mean, we don't know yet how many. There are these giant black holes in the middle of galaxies, and then there are smaller black holes caused when massive stars dies. And our galaxy probably has millions of those. But the ones in the center of the galaxies are fascinating. The one in our galaxy, so we're about 25,000 light years away from this guy, so we're safe. But we actually observe stars that are trapped around the black hole that are orbiting the black hole. This was the first way we found the location of the black hole. Stars were orbiting kind of like this angry swarm of bees almost in every direction, and they were orbiting around something you didn't see. And the mass needed to make all these stars orbit was about 4 million times the mass of the sun. There was a star called S2 we observed orbiting close to the black hole, kind of like a comet. It would come in and whip around the black hole, then go back out again. And an S2 at closest approach, when it whips around the black hole, this is a star, goes nearly 20 million miles an hour as it whips around the black hole. And then just recently we found another star that actually gets up to over 50 million miles an hour as the black hole whips it around. And this is how we test the idea that time is different around a black hole. We actually see these stars whipping so close to a black hole, we can tell that there are changes in their orbit, that they're actually going through different time. And so we see these stars whipping around the black hole in the middle of our galaxy. They will probably eventually go down that black hole. I mean, maybe everything in our galaxy will eventually kind of spiral down into that black hole. But, this is not conjectural. These are observations from telescopes. Look up S2. Look up, I don't know what the name of the one that goes faster. It's a telephone number. But that's real. Now, the question about what happens if you could survive going into a black hole, and this is another place where we need better physics. Quite honestly, our physics gives up. There are all kinds of wonderful, fascinating possibilities. I mean, people have pointed out this is not observation. Now we're going from observation. We see these things. They're real to conjecture. People have said that if you take the entire universe, the entire mass of the universe and the radius, the diameter of the observable universe almost exactly matches a black hole. Could it be that, inside a black hole, a new universe forms when a black hole forms? Is that what the Big Bang was? Was the Big Bang a black hole forming in another universe and popping off our own universe? Are black holes somehow connected to other universes? These are all incredible questions. We don't yet have the physics to answer them. But, people have said, why is it the universe has about the same density of a black hole, the same size and mass? Is that just a coincidence, or are we looking at something deeper?
Or is it fractal? Is it the entire universe exists inside of a black hole?
Yes, exactly.
That's bananas.
Yeah, there we have the Very Large Array. That was at the that was in Chile. That's a wonderful observatory. There we have a great depiction. Oh, you found okay, yeah. So
I've never seen a depiction.
That's
like
right.
This.
That's the stars moving around a black hole.
Yeah, the
That's
stars moving around a black
bananas.
hole.
What's coming? What would this ejection be?
So that what that is that's a consequence of the black holes that doesn't come from inside the black hole. All of that swirling gas gets really fast. We actually observe some of the swirling gas going close to the speed of light. Black holes, they're going down the drain. They're going faster and faster as you get closer to the black hole. And all of that very, very hot gas generates a very strong magnetic field. And so what you're looking at with those jets is that that's just the magnetic field of the hot gas going around the black hole. Some of that hot gas gets directed into jets by the magnetic field. There's nothing coming out of the black hole. Nothing that we know of comes out of a black hole. But black holes are incredibly, this is wonderfully ironic. They're incredibly bright because if there's gas trying to get around, spinning around a black hole, the gravity accelerates that gas so fast, it spins it up to, in some cases, millions or billions of degrees. You can see them clear across the observable universe. They're the brightest objects in the sky. And this is not light coming from inside the black hole. It's light coming from stuff trapped around the black hole as it spirals in. And these huge jets, we see some of these jets going, in some cases, more than 100,000 light years. I mean, they're huge jets that come out.
100,000 light years, and 1 light year is how many trillion miles?
6 trillion miles about. Yeah. So.
Oh my God.
And then in the.
Oh my God.
Yeah. So I mean, around
that video is so nuts.
I've never seen that.
Yeah.
When I was looking for this or stumbled across this, I saw a theoretical thing called a white hole. Which is potentially maybe on the other side of a black hole.
No. It's an idea. I mean, that idea, honestly, it had a lot more following. More in like the 60s and 70s. It's kind of fallen out of favor because at first we thought that these hugely bright objects were white holes. At the end of a black hole, maybe the radiation went through a tunnel through space, then came out somewhere. But now we know that these super bright objects are actually hot gas disks around black holes, and they are bright. Like I said, they're the brightest things we know of in the sky. And, so that's something you can see, literally billions of light years away is the hot gas going around a black hole.
You said another thing that broke my brain. You were talking about what the Big Bang is, and that we shouldn't think of the Big Bang as an explosion, but that before the Big Bang, time and space might not have existed.
Well, pretty much certainly not in the way we experience them, no. I mean, once again, no astronomer thinks the Big Bang came from nothing. The problem is, once again, we have no description of what that state of matter would be. None. I mean, the idea that everything we observe of in the universe could have once been at a subatomic scale. You'll notice I'm very careful about this. I talk about the observable universe. We have no idea how big the universe is. We don't know whether it's infinite or whether it has an end. But there's been only a certain amount of time that light has had to travel to us. That's not the whole universe. That's centered on us. That's an effect of we look in every direction in the sky. We can only look back as far as there's been time for light to actually travel to us. And you see some incredible things. I mean, one of the things that one of my friends has the Nobel Prize for is if you look so far away, the farthest away we can see now, we're looking back to a time about 400,000 years after the Big Bang. And this is something where we are actually able to see so far away. We're looking back to a time when the whole universe was hot and bright. It actually was glowing like the surface of the sun, the whole universe. The entire universe was so bright, it was like looking at the surface of the sun. And this this radiation has traveled a long time to get to us. It's now lost energy because it's traveling through the expanding universe. And as the universe expands, the wavelength of light gets stretched out by the expansion of space. This is what we call the microwave background radiation. So there's a microwave, very low energy signal. It comes from every direction on the sky. And it's coming from a distance so far away that the whole universe was as bright as the surface of the sun. And that's as far as we can see, because any farther away from that, the universe is opaque. Literally in every direction on the sky, you eventually look back to a time when the whole universe was so dense and bright, you can't see any farther.
Is this because of how we're capable of measuring? And is it possible that at one point in time, when we get better and better telescopes, that we can look past that?
Well, not with light. See, the universe actually does become opaque to light at that point.
Because it's too long ago.
It's basically, the universe is so bright itself. Yeah. I mean, so, you look in any direction on the sky, you look back to a time. The wonderful thing about the universe changing is we know this is true. The farther out we look with a telescope, the farther light has had to travel, the more time it takes to get to us. So the sun, we see, the light takes about 8 minutes to get from us to the sun. The nearest star, about 4 years. The nearest galaxy to us, about 2 million years. We can see so far away in space that the light took pretty much the age of the universe to get to us, about 400,000 years after the Big Bang. At that point, the universe becomes opaque to light. So there is a limit to how much we can observe with light, how much time there has been for light to actually get to us.
Is there a potential for being able to observe something other than light?
Absolutely. So your question is a really profound one. We don't know how big the universe is. When we talk about the universe, we mainly talk about the observable universe, everything we're able to see. So the question you just asked, can you see farther back, even if it's opaque to light? Yes. And this is something that, again, we talk about moments in your life where the universe changed, where you thought people did something you thought was impossible. And going all the way back to the mid-'90s, I was a postdoc at Caltech. And I wasn't working with this department, but people were starting to measure something called gravitational waves. And gravitational waves, again, I never thought they'd be able to actually detect these. The universe is constantly, every time we move, remember how I said time is different from the top of your head to the bottom of your feet. As I move, I create gravity. Gravity actually it goes out as a wave into the universe at the speed of light. Can you detect a wave of gravity? Well, gravity is actually a curvature of space and time itself. So you're trying to say, could we detect a wave that's actually made of space and time? And this project is called LIGO. And LIGO stands for the Laser Interferometric Gravitational Wave Observatory. And it started out with 2 facilities, one in Oregon and one in Louisiana. And LIGO has 2 extremely long lasers at a corner, at a right angle. The lasers, I believe, are 4 kilometers on a side. They're huge, right? A 4-kilometer laser. They want them to be as perfectly the same length as they can. And then there's a laser beam that bounces back and forth. And as the laser beam bounces back and forth, if it's exactly the same length, the signal kind of cancels out. But what happens if there's actually a wave of space and time coming by? Space itself compresses, time changes. All of a sudden, these two lasers are no longer exactly the same length. Space itself has changed as a wave comes by. Tiny amounts. These gravitational waves are thousands of times smaller than the nucleus of an atom. Incredible, right? How would you detect that? And they're traveling at the speed of light. So you have these 4-kilometer lasers. A wave of space and time comes by and compresses space and time in one direction more than the other. All of a sudden, the lasers are no longer the same length. You get a signal. The noise for this, right? Every time, so this is us detecting an exploding star this way. I'm happy to talk about that too. But just the fact they did this, These lasers are under vacuums. They're in vacuum chambers. I mean, they try. I mean, every time the UPS truck goes by, they must go haywire. Somebody sneezes. They're measuring things thousands of times smaller than the nucleus of an atom. But over time, they got this so accurate. They did it so well that what happened, and you can look up the year, but it was something on the order of about 10 years ago. A long ways away, millions of light years away, two black holes spiraled together and actually collided to form a big black hole. That was a lot of gravitational energy, and that created a ripple going out into the universe. And so, there's all of the detectors have all this noise in them. The detectors are detecting all kinds of spurious signals. But then all of a sudden in Louisiana, there was the whole detector went whump, 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 boom. And then at the speed of light, the detector in Louisiana did exactly the same thing. Whump, 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 the exact same waves at the speed of light difference. And we realized, oh my God, they did it. These tiny waves, we shouldn't even be able to detect them. They found them, and now it's a routine thing. They've now done this many, many times. Waves in space and time itself might be the way we can see even farther back into the universe. Even when the universe becomes opaque to light, the waves of space and time can come through. Gravitational waves can come through that. And if we can somehow figure out how to make these detectors better and better, could we detect the gravitational waves of the Big Bang? Can we learn something about that moment by the way it actually bent space and time and created waves of gravity? And once again, just step back a sec. Detecting waves of space and time traveling at the speed of light is something we do. We've done this. It got the Nobel Prize. It deserved it. There were hundreds of people on that first paper. Some of them were friends of mine. Again, they fucking did it. I cannot. I felt my heart just drop that day. Out of joy. It's like, holy fuck, they did it. That may give us the potential to understand the Big Bang better as we get better with that. Maybe we can. Right now we see black holes colliding. We actually see neutron stars colliding, even stars orbiting each other. Maybe produce a sort of a background of all these waves. But maybe we'll be able to figure out how to see those waves from the moment the universe began.
How are we sure that of the timeline of 13.8 billion years or whatever it is?
Well, these things are never sure, absolutely. But there's some very good reasons to think it's about that. So, you sort of run physics backwards. You basically say, this is how the universe is expanding now. And let's roughly say that things came together. And as I mentioned, you mentioned the podcast, the Big Bang did not have a center. The galaxies are not flying off into space like an explosion. What happened is the galaxies are all kind of sort of standing where they are, but space itself is expanding in every direction between the galaxies. It's a hard thing. It's a huge misconception about the Big Bang, that the Big Bang was this explosion and galaxies are flying into empty space. The expansion of space is space itself. There's no space out there that galaxies are flying into. That's not how it works.
Right. That's a weird thought right there.
Yeah,
that they're not flying into space; they are space.
When I used to teach this, I used to take a board and I used to have a piece of elastic, and I would hammer two nails in on either side of the board, and then I would say, okay, these two nails are galaxies. And the elastic between them represents our universe. In this case, a two-dimensional depiction of our universe. All of space and time, anywhere light can travel, is just on that elastic. Don't think about up or down. There's no space or time there. Everything our universe is just this piece of elastic. And then I would take the elastic and I would stretch it. And I would say, the two galaxies aren't moving. They're kind of sitting there. It's the space in between that has now stretched, has now changed. And that's a more realistic idea. The galaxies are not flying through space. It's the space itself that is getting bigger in every direction at once. And that's why there's no center. There's no empty center to the universe. The universe, as far as we can map it, has galaxies everywhere. There's no center to it. The expansion is happening in every direction at once because the elastic of space and time itself in every direction is just getting bigger. We don't know why.
So if we are looking at something where the Big Bang created space and time, and as space and time is expanding, what was the environment before the Big Bang?
Yeah, and that's the problem. So you mean we have no description of that. There are particle accelerators. I've had the wonderful chance to go to CERN a couple of times and go to the Large Hadron Collider, and using incredible accelerating magnets. They whip just single protons up to very, very high temperatures. I mean, they're trying to recreate conditions where they can't recreate the conditions of what things were like before the Big Bang, but can you get matter to such a high energy state that it can recreate what things were like a millionth of a second after the Big Bang, or maybe even further back, and but the idea of what was that state of matter before that expansion, we have no description of yet. I think we will someday. I don't think it's impossible. But there's nothing about our current physics. I mean, it would be like taking somebody from the 1400s and saying, describe to me what the interior of the sun is like. They would have no knowledge structure to even attempt it. That doesn't mean we didn't figure it out eventually. And, so like I said, there's nothing about that I think that's completely off limits, but we'll have to understand space and time very differently. And we'll have to understand what, you can't even really call it matter or even energy. All of the energy of the universe in a subatomic space, we have no idea what that would behave like.
And what is it existing in?
Yeah, well,
that's what I'm asking is like the environment that preceded the Big Bang.
Yes.
Like, what are we talking about? Where this subatomic thing that contains everything that's in the known universe.
Yeah.
What is it? How is it existing?
And of course, I have no answer to it. I mean, you're asking the question that I hope someday humanity will have a chance to explore and we'll know more about. Then I think what will happen is that once we can describe what happened before the Big Bang, there'll be a whole series of other questions.
So if the Big Bang is the wrong way to think about it, of a bang, what's the right way to think about it?
Yeah.
The initial expansion?
I can't think of necessarily a better term. I mean, the Big Bang was meant as actually a criticism, right? It was Fred Hoyle. When people first began, back in the 1920s when they discovered the universe was expanding, and this was a big surprise. I mean, famously, Albert Einstein didn't think that it was. And then he saw the evidence. All of a sudden, with our telescopes, we saw the universe is expanding in every direction. It was actually Fred Hoyle that, said at a conference as a way of making fun of this. People were saying, well, maybe everything went back to sort of a common, denser, structure. It was actually a Belgian Jesuit father, a Belgian priest named Georges Lemaitre, who came up with the idea that if the universe was expanding now, if we run time backwards, maybe it all becomes one big. He called it the primordial atom. That was Georges Lemaitre. And like I said,
what year was this?
Georges Lemaitre. So we would have been talking round about probably sometime in the 1920s. I bet we could probably have some help.
So 100 years ago.
Yeah, 100 years ago. So Georges Lemaitre says if we run time backwards, we get this big lump of something, the primordial atom. And then Fred Hoyle said, "What, you mean the whole universe started with a big bang? Really? There was this atom that went bang." So even the term the Big Bang was meant as a criticism. It was meant to be funny. It wasn't something that scientists came up with as the best description. But what happened then is everybody kind of nodded and said, well, yeah, and I mean, more people should know about Georges Lemaitre, the Jesuit Belgian scientist that came up with that idea. I think he was a fascinating man. Interestingly enough, even as a Jesuit, he did not think that this necessarily was a biblical Genesis story. I mean, he was approaching this as a scientist. What's the best thing we can say about to describe these different times and states of the universe? A lot of my friends are the Catholic Church. The Jesuits have had an active astronomy program for 1,000 years, and so the Vatican Observatory still has an excellent program. So, but the question you're asking about what came before the Big Bang, I mean, again, what happens inside a black hole? It's wonderful that there are these things right over the horizon from us. We know the universe is expanding. What was it like before? What a great, simple, elegant question. We have no idea yet.
Why do we think that it was so small?
There's some interesting evidence about that. And once again, it's not so much that the entire universe was small. There's compelling evidence that everything we can see was once in a very small volume. Let me just sort of say that. We're limited by this time factor. You look out as far as you can, and eventually you get to the time of the Big Bang. You can't see any further. The universe to us is only as big as light has had time to travel to us. That's not the whole universe. If you're on a galaxy billions of light years away from us, that galaxy sees its own observable universe. We basically see in a sphere around us how far we're able to see given the time. A galaxy that we can observe with the Webb telescope has its own sphere around it. It's seeing into the universe farther than we can see in some directions. So we know the universe isn't just our observable universe. So like I said, we're here. We can see as far back as light has had time to travel to us since the Big Bang. But then there's another galaxy over here, and it has its own view. And then there's another one over here that has its own view.
Here, Jimmy put something up here.
Yeah. So, yeah, I'm not even sure that. That's a great NASA depiction of where this. You see, as you move toward the left, back to the time of the Big Bang, you get to this kind of beautiful, kind of rainbow-colored area, and that's what they call the afterglow. That's the microwave background radiation, about 400,000 years after the Big Bang. That's as far as we can see. The universe after that becomes opaque. So that's as far as our observable universe can take us. We know that's not the whole universe. So the whole universe could have been huge before the Big Bang. It could have been infinite. We don't know how big it was. All we know is our little bit of it. For the sake of argument, let's say I'm the entire meta-universe. There was a little atom of me that expanded to become the known universe we know. But that doesn't mean that little atom was the whole universe. The universe could be huge. We don't know. Before the Big Bang, it could have already been infinitely large. We have no idea. The only evidence we have is that the stuff we can see was once in a very close area. And that goes back to that radiation, that microwave background. The microwave background has been a wonderful story. It was discovered back in the 1970s by two scientists from Bell Labs called Penzias and Wilson. And they were trying to categorize. They were dealing with Bell Labs. They were trying to deal with microwave signals, microwave communication, and they built a big microwave telescope. And they started to catalog what objects in the sky naturally produce microwaves. The sun produces some. Other things produce microwaves. This was all for communications. And they discovered that everywhere they looked in the sky, there was this background noise, very low level, but it was there. Everywhere they looked, it was the same. Didn't matter what direction the telescope was pointing. And so what a good scientist would assume is that that's probably a problem with your telescope. If you have background noise in every direction you look, it's probably in your detector. And the best guess they had was that it was pigeon shit. So there you go, pigeon. Look at that.
Wow.
So Penzias and Wilson built this. They were working with this big microwave telescope, and little did I know that pigeon shit actually gives off microwaves. It does. They trapped all the pigeons in the microwave telescope. You can actually see a pigeon trap in the Smithsonian where they did this. They scraped out all the pigeon shit, and lo and behold, the signal was still there. In every direction you looked, it was exactly the same. Exactly. And what they had discovered was the afterglow of the Big Bang, the energy left over from that time when the universe was so hot, it was opaque to light. And the crazy thing is, it is exactly the same down to fractions of a degree in every direction on the sky. It's sort of like, you look all the way the age of the universe in one direction. It's exactly the same temperature as the age of the universe in that direction. And there shouldn't have been time for those two areas of space to ever get to know each other. There shouldn't have been time. It's like, everything came to the same temperature everywhere you look. Why? It's sort of thinking like if I have a coffee cup, the coffee cup eventually comes to exactly the same temperature. Everything becomes thermally equilibrium. Everything comes to the same temperature. You wouldn't expect your coffee cup to be like, 300 degrees on one side and, minus 50 on the other. Somehow, the universe had a chance to all come to the same temperature even though those areas of the universe were so far apart they should never have had a chance to touch each other. And that became part of the thinking that maybe at one point when the universe was that large, things were much smaller. The universe did have a chance to come to this exact same temperature all over. Boy, I hope I see by your expression I should do a better job of explaining this.
No, you're doing a great job. It's just absolutely fascinating.
Yeah.
My expression is just perplexed.
Yeah, well, no, so this is one of the best proofs that things were small. That you look back to this microwave background radiation, and we're talking fractions and fractions of a degree. The first NASA satellite that observed it was called COBE, and then they're the Cosmic Microwave Explorer. And then there was a new one in the 1990s called WMAC, the Wilkinson Microwave Anisotropy Probe. Oh, yes, good. They measured this, down to hundreds of thousands of a degree, right? I mean, they measured it to tiny little amounts. And the incredible thing was that it was almost exactly the same temperature, but there were these beautiful, large. There were variations in the temperature, and the variation in the temperatures corresponded to sound waves propagating across the whole universe at that time. It's deep. It's wonderful. I highly recommend you read about this. We have this signal that comes back from basically the first moment the universe became transparent to light. It was so dense, it was opaque beforehand. There was a moment light could finally freely fly through the universe. And we found that. We found that signal. It goes back to a time about 400,000 years after the Big Bang. And it is breathtaking in its profound nature. You can actually see sound waves go across the whole universe.
Wow.
Yeah.
Wow. Now, when we think of the Big Bang, we think of it as almost being an instantaneous event.
Well, yeah. I mean, again, you, as an experimental scientist, there are all these wonderful theories about what things happened like a millionth of a second and a billionth of a second after. And I'm going to take all that with a grain of salt. I don't think we understand it well enough to be all that confident about that. There's a great book called The First 3 Minutes, which has been around since probably since the 1970s, maybe even longer. And it sort of outlines how we think that the universe in the first 3 minutes basically went from the Big Bang to just sort of all the hydrogen and helium that we have. And in the first 3 minutes, it pretty much everything was done. The whole sort of process of the Big Bang was done in those first 3 minutes. The actual Big Bang itself goes back to something called the Planck epoch, which you see there, 10 to the minus 33rd seconds, 10 to the minus 43rd seconds. So take a decimal point, draw 42 zeros, and then a 43.
Singularity, infinite density, and temperature. Quantum gravity dominates. Sure. Forces unified.
Absolutely. Again, big chunk of salt there. Yeah. I mean, so this is not bullshit. This is the best model given our understanding of modern physics. Do I think this is right? Literally, no. I think we've got a lot to understand about how gravity works in high density situations. When gravity and quantum mechanics come together, those two theories, they don't work well together. And in order to understand how things were like right before the Big Bang or even right after, I think you need to understand that a lot better. I mean, all this stuff that we think may be dark matter and dark energy, none of that is in the current theory of how the Big Bang started. We don't know if it's important or not. That's a good first step. You have to take your current understanding of physics and take it as far as you can. But in the case of what happened right at the instant of the Big Bang, I don't think we're there yet. I think we need a better understanding of what happens when you have that amount of density in such an entire space. It's like the interior of a black hole. We don't have the physics to describe high density, high gravity conditions.
Insane high density.
Oh yeah.
I mean, to the point where you can't even
take the known universe and put it inside the nucleus of an atom. Yeah, we don't got that yet.
And what is it in?
And are there others? I mean, some of the best ideas about the Big Bang is that the expansion never stops. It kind of pops off universes, like you said, almost fractally all the time. That's the idea of Alan Guth. That's the idea of Alan Guth's idea. Well, it's not the expanding universe. I'll come up with it later. But back in the 1970s, a man at MIT, Alan Guth, had his theory of how this expansion might never stop. So we don't know that. That may absolutely. There you go. Inflationary. Sorry, that was a complete mental fart. I know the inflationary universe, but again, I think all of this is a necessary first grasp using our current understanding of physics. I don't think we understand how the Big Bang went off yet. I think we need a ways to go.
Well, it's got to be so fascinating to you to know so much, and yet still have so many things that we have no idea.
You know, that's I think you've just hit it on the head about one of the most beautiful and one of the most frustrating and even scary things about being a scientist. You have to be honest about what you don't know. I mean, you have to say, we made this measurement and it's real. You know, we fucking managed to see the event horizon of a black hole. We caught the same wavelength of light over, thousands of miles. You can say what's real. And then you can say, these are the things we do not know. And they are major. How did the universe begin? What happens inside a black hole? What happens inside a neutron star? We don't have the ability yet to know. And it's hard for humans to stop there. And of course, we make better experiments. Find a better theory of physics. But for the moment, you need to sit with that uncertainty. There is no one who knows what happened. And there are so many things in our life that I've had to confront where you have to become comfortable with stopping there, at least for now. I do not understand this. I do not have the answer to this, and I don't think anybody does. And I think we'd actually benefit a lot more in humility and joy and maybe even compassion with each other, if we can respect that stop. And say, you may not have the same answer as to what comes next about life or death or the beginning of the universe or the inside of a black hole. We can respect each other. To me, I find a good discipline and the humility to stop and say, I don't know.
Well, it's very important because otherwise we're not going to believe you with the stuff that you do know. There has to be some things that you can't know.
It has to be measurable. So,
yeah,
and this
especially in the current state of what we're able to measure right now.
Science is limited deliberately. And I think this is beautiful. I think people don't understand. There are things that are outside, at least for now, the realm of measurement. And that doesn't mean they're not real. As a scientist, I cannot say that there aren't, ghosts or, inside a black hole or alien visitations or whatever. There are all kinds of things that are wonderful to think about. What can you do a consistent experiment on that people all around the world could do the same experiment and get the same result? That's science, and it's limited. I've had to talk to so many people that called into NASA saying they had profound experiences with time travel. Or
you had to talk to time travelers?
Oh, yeah. Or people would call in.
Was there a time traveler hotline like Art Bell?
They would often forward the calls to me. And,
why you?
Well, I was doing communications at NASA, and I think they just didn't know what to do with these people. And I think they knew. And I pride myself on this. I try to be kind. I try to lead with compassion. And I would listen to people's stories about, I traveled in time or I was abducted by an alien or many things. And, and I would listen to them. I think that what they mainly wanted to do was find somebody to listen. I would say to them, you have had a profound experience. You have experienced something that, I hope you view as a gift. I would say that there's not much as a scientist that I can do with an individual experience. I can't do an experiment on it. I can't have my colleagues all over the world do the same experiment about what did you have a spiritual experience? Did you have a profound feeling of oneness? It's not that these aren't real. Science has to be limited. Because just like what you said, how can you trust it, right? How can you trust people are saying, why are these people at NASA allowed to have telescopes and do all this stuff? What makes this worthwhile? You have to say there's a limitation. What do we have clear evidence on that everyone could do the same experiment and get a similar result? That doesn't mean other things aren't real. It means that science is limited to what is reproducible, consistently reproducible. And what a human experiences could be profound and real, but at the moment, not in the realm of science.
So you're not discounting the possibility of people having profound experiences, but there's really no way to measure it
At the moment, no.
at the moment.
I mean, maybe when we understand the brain better, maybe if AIs are sharing minds, I mean, we're talking, incredible, fun conjecture here. At the moment, we're limited with the tools of what is reproducible. I mean, if you observe in one direction with your telescope for a certain amount of time at a certain wavelength of light, you should see pretty much the same thing. Whoever does the experiment. If you're doing an experiment with atoms or quantum mechanics or whatever, it has to be reproducible. That doesn't mean that profound things that are real are not there. They're just not in the realm of science right now.
When you're communicating with people that supposedly have had experiences with intelligent life from somewhere else, and you spend so much time looking up at space, like how much time and how much effort do you spend even considering that possibility of life somewhere else, or of whether or not these people have actually experienced visitation, or whether or not it's some sort of mental illness, or whether there's some kind of an experience that's available to people occasionally here that defies our understanding of what is measurable and what's reproducible, that
Absolutely.
there's something else out there?
I think that's a wonderful question, and I think this may give you a little bit of a snapshot of the culture of science and a mind of a scientist, because it's an odd little tightrope to walk. I'm very proud of it, actually. I think it's kind of beautiful. All of us, to a person at NASA, thinks that there must be life out there. The idea that there's only life on the Earth seems untenable. I mean, not only do you see the billions of stars in our own galaxy, but we see billions of galaxies. How could it just be us? How could it? We're all science fiction fans. We all love the idea of there being life out there. I always keep a bottle of champagne chilling. I have for decades now, in the hopes that someday we'll have a clear evidence of life outside the Earth. We'll have a signal that we.
What are you willing to pop the champagne for? Is it molecules? Is
I'd
it bacteria?
Well, definitely bacteria. I definitely pond scum, some little microbe on Mars. You got it. Like, the champagne is coming out. And at the same time, there are the fantastic scientists of SETI, the Search for Extraterrestrial Intelligence, who are scanning the skies looking for mathematical signals from civilizations. The question for me comes down to, again, what is a reproducible observation? And with the advent, the recent release of these videos from fighter jets and all of that, I think an interesting thing is that scientists at NASA, and the universities, we're not getting together over a beer and looking at these videos and really getting excited. It's not enough yet. We're seeing these things we can't explain, but we're trained as skeptical scientists to sort of stop there. Okay, we can't explain this. That next step, that this is an alien, we're not willing to go yet. We need more evidence than that. But as I said, that's a deliberate training of a scientist, is that skeptical stop. The people who have had experiences, and no, I'm not willing to dismiss them as being mentally ill necessarily. I honestly don't know what it is they experience. It is certainly within my realm of possibility that what they're describing actually happened. I cannot say that that's impossible. What I as a skeptical scientist, I'm stopped by. I would need more evidence than an individual experience. This happens in many aspects of life. It's not just the visitation of extraterrestrials. I have people that are extremely trustworthy, who would never lie, who have had profound spiritual experiences. They have experiences of an afterlife and of people living on after death, and of being able to communicate with people. And that is not part of my experience. But these people are completely, 100% trustworthy. I have to live in this universe where I don't get to say what's real and what's not. These trustworthy people have experienced something profound, and it may be real. It may be that they've seen people after they've died, or they've seen, visitors from other planets. That gives me joy. I sure hope we live in a larger reality that I'm aware of. As a scientist, I pull back and say, it's not my experience. It's not something I can measure yet. And so I live in this hope that someday we'll have more proof. I live in this hope that someday there'll be a signal we know is artificial. We see something we can't explain otherwise. We are visited clearly. I live in this sort of skeptical tightrope with hope that someday things will become more clear.
That's a great place to be. I love that.
I actually like it. To me, I think humility and compassion. I think the world could use a lot more of that.
For sure.
Yeah. Reserve judgment. Think about how different a human experience is. We don't understand what consciousness is. We don't understand how the human brain works. Is it possible somebody had a different experience of time? Maybe it is. In science, what can we measure is powerful. We do things we should not be able to do, like catch waves of space and time, see light and space curve around a neutron star. And that's real. That's a measurement. Stick a pin in it, it's done. And leave humility and compassion for the experience of other humans.
How much are we limited by our senses?
Oh, yeah. Is space and time a construct of our brains, actually? Seriously. For a while now, ever since the late 1700s, we've known that there is light that our eyes don't detect. Mind-blowing. The human eye only detects a tiny amount of light that exists in the universe. Colors of light, that our eye just doesn't detect at all, are real. Some of the first measurement was William Herschel back in the late 1700s. He discovered infrared radiation. Is it even deeper than that? Are there, as I said, friends who have experiences with people who are dead? Are there people that are sensitive to that and other brains are not? Maybe. Is it possible that people have very different experiences of reality? I will admit I'm a chicken. I've never actually done any hallucinogenic drugs. I have been tempted, because I do sometimes wonder if under that sort of influence, the filters of our brain are different. Could you actually have an experience of something that could be real because your filters, how we perceive space and time in the universe, are changed by the drug? Like I said, I'm too much of a chicken, but I've always been curious about that. Is it possible different people have seriously different ways of experiencing the universe? Yeah, it may be.
What about it makes you a chicken?
I'm not sure I trust an unleashed mind in my case. I have, I think there are people who suffer or are gifted by very extreme dreams. I'm one of them. I'm often exhausted by my dreams in the morning. Actually, I had a night last night. The dreams were a lot to recover from, and I'm a little worried. Sometimes my dreams are wonderful, and sometimes they are horrible, and I remember them forever. There are things I really would like to erase that I've dreamt about. I'm not real confident in letting my mind be unfettered. Yeah.
Why do you think it's unfettered? What about a psychedelic a psychedelic experience makes you consider it as an unfettered mind?
I guess that may be sort of the propaganda of the good and bad trips, right? People sometimes have wonderful experiences and sometimes very terrible ones.
Do you know why though?
No.
It's control. You're trying to control it for the most part. Most people that describe bad trips, they're trying to resist it. Because you're flooded with anxiety and fear and the unknown, and it seems very strange, like bizarre, beyond reality. But one of the craziest things about the most prevalent psychedelic is that the mind produces it, which is dimethyltryptamine. The brain produces it. It's produced in the liver and the lungs. It's very, very weird. The most potent psychedelic known to man is actually made by the human body.
Fascinating.
it's one of the weirdest ones too because your body brings it back to baseline very quickly. It's a very quick experience. It's like 15 minutes. And they think part of the reason why your body processes it so fast is because it's endogenous. It's so common to the human body that your body gets this big flood of it and it's like, oh, I know what to do with this. And it brings you back to baseline very, very quickly. The weirdest part about that experience is that it feels way more real than reality itself. And that's what everybody describes. So you might be correct in that what these things may be able to do, especially something that the actual body, the human body produces on its own, that you might be able to experience things that are there all the time, but you just lack the ability to interface with them.
Yeah.
Because there's some sort of a chemical gateway that's opened by these things.
I can entirely believe that. I mean, again, stepping a little bit away from science into conjecture, that makes perfect sense to me. I mean, physics shows us that time and space are not the way we perceive them. We know that. We don't know what they are, but we know they're not a simple flow and, space is just nothing. I mean, we know space and time can bend and change. And so the idea that our brain filters this somehow, entirely possible, and that people may have slightly different filters. I mean, I think
well,
that's...
I always wondered that about schizophrenics.
Yeah.
Like, what are they experiencing? Are they in a constant dream state? Like,
Yeah.
really profoundly schizophrenic people that are they're having voices and communication. Like, I don't want to do it, but could you imagine if you got some guy ranting and raving on the street corner, if you say, just let me in there for 5 seconds.
Yeah, what would you
just
see?
give me 5 seconds.
Yeah.
What is reality like to this guy, and what's wrong? What's wrong with his interface? What is happening with him he's seeing things that none of us see. He's experiencing things that none of us experience, but he's doing it all day long, constantly. He lives in a crazy fantasy world.
Well, I may be interested. I mean, I've also, not just the experience of physics, and people have talked about being able to see colors and, see sounds and hear colors. I think that would be fascinating. But a lot of people have talked to me as well about the benefits for grief. And, that's something that, I got knocked on my ass by grief. I still am. I'm trying to figure out, how you sort of get beyond that. And I've heard as well that psychedelic drugs can be a treatment for that.
Yeah, it's a lot of it is also for people that have end-of-life anxiety, people that are dying from cancer, particularly psilocybin, for some reason, has a profound effect on people, like experiencing it and letting it go. Do you remember that show Dallas?
Yeah.
Remember, I think it's Larry Hagman?
Yeah.
Is that what his name was?
Yeah.
So he was on CNN once, and he was talking about life and death, and he said that he had an experience on LSD that completely released him from his fear of death. And it was the most bizarre CNN interview ever.
Sounds fantastic.
Yeah, I know, but they're saying, I don't think they expected J.R. Ewing to say this. The guy from Dallas who was like this bad guy. Here it is.
Yeah.
Talking to Joy Behar on Headline News. It's very,
Yeah.
Oh, it's headline. Is that CNN?
It's some very similar.
Okay.
We're owned by the same people.
I would like that. I would like to lose my fear of death.
Listen to what he says here.
Crosby, Stills, and Nash turned you on to LSD. What was that like? Tell me a little about that.
Oh, how much time we got?
About a minute. But you can do a lot in a minute.
A minute.
Yeah.
Okay. It took the fear of death away.
Really? That's a great
That's a big
answer.
one, yeah.
That's a great answer. But did it hold?
Yeah.
Do you have to keep taking it
Did
to
it
not
what,
be
it hurt?
scared? No, did it hold? Did the lack of fear, the losing the fear of death?
Oh, yeah. Oh, sure. Absolutely. Once
So-
you've lost the fear of death, it doesn't matter.
How did it, what happened to you? How did that manifest?
Oh, my dear. Have you heard of the white light? Have you ever heard of that?
Only when I'm going into Jersey.
Well, I went into this place that was the white light, where everything's okay.
Well, I think that's worth
I think,
taking. Yeah.
And I think it ought to be mandatory that all our politicians should do it at least once.
That's a good suggestion.
I think Joy should do it too. Should quit The View.
Can you imagine being in an interview and somebody's like, "You got 30 seconds. Tell me about the most profound experience you've ever had."
Yeah, that's the most ridiculous aspect of those shows.
Wow.
Is that they're constricted by time.
I like that idea though, and I like the idea that it could help us through things like that. I really do. I mean, I know psilocybin was legal in Washington D.C. when I was living near Washington D.C. When my husband died, and I really wanted to. I really wish somebody could have made him be happier. I was like, should I just go get some? And I didn't, but I thought it should be a therapy, an optional therapy.
Yeah.
That could be something that you give people to help them through that.
Well, we are very restricted by the propaganda that made all that stuff illegal in the first place, unfortunately. And, I recently went to the White House to help make these things available for veterans and for first responders and people dealing with traumatic experiences. Because the only reason why they were illegal was because of the Nixon administration, the Controlled Substances Act of 1970. And what they did was they were targeting the civil rights movement and the anti-war movement, and they knew that these people were taking these kind of drugs, and this was part of the fear of like the hippie movement and all these people. And so they just made all these things Schedule I, meaning they had no medicinal use whatsoever, highly addictive, very dangerous. And it's not true. It's not true. I mean, you can't eat enough mushrooms to die. It's not even possible. I mean, you'd have to eat pounds of it, and most people are going to live even then. It's not what they think it is. It's not what they said it was, and they inundated our society with this propaganda that's taken more than 50 years for people to escape. It confused the shit out of everybody about what these things really are, and that's why you have this fear of the unfettered mind. I don't think you should have that fear.
I like that idea.
You also could take a microdose. If you found someone who could get you some, take a microdose, and I think you'd enjoy it profoundly. And it wouldn't freak you out at all. A microdose is it's like a sub-psychedelic threshold dose where you just feel better. You just feel wonderful. You just feel nicer. You feel like you have better spatial awareness, which is weird, better edge detection. It's very strange, measurable. They did these studies, I think it was in the 1960s, where they gave people psilocybin and then they had a control group. And the people that were on psilocybin were able to detect when parallel lines varied quicker than the people that were not on psilocybin. So they had these parallel lines and they slightly deviated. The people on psilocybin were able to detect it much quicker.
Yeah.
Which is weird.
Well, I mean, to me that makes sense. I mean, I can imagine that, if the brain is stimulated in certain ways, it would act more efficiently. It could, sure. I mean, that works with me. Yeah.
Well, the weirdest thing about it is that when they do brain scans of people on psilocybin, it doesn't show a stimulated brain.
All right.
It shows a quiet brain.
We understand so little about the brain. I had a friend who was a neuroscientist at Caltech, and one of the things he really I loved this quotation. He said that we always compare the brain historically to sort of what the height of our technology is. The Romans thought of it as sort of a series of fluid aqueducts, and then in the 18th century, you had the idea of gears, cogs, cognition, right, where we get that word from.
Wow.
And clockwork was their highest form of technology, and then we compare it to a computer. And it's probably about as much of a computer as it is a clock, right? I mean, we do not understand yet how this works. Yeah. We have no idea what the mechanism of memory, or how. Why do we perceive space and time the way we do?
Right.
If the universe really does exist in a huge infinite now, how can we think one event causes another? How can we think time progresses? These are fascinating questions about our lack of understanding of what the brain is at all, how it works. I'm sure when we understand quantum computing better, we'll probably say it's a quantum computer. However technology progresses, we're always comparing it to the height of our current technology.
Yeah, and when we interface with technology, does that give us a better understanding of how we fit into this thing? Or do we just have more capability? And are we still burdened with the same questions? Just, where's that quote? I think it was Dennis McKenna's quote of the bonfire. Once the bonfire of information is lit, it exposes more surface area of ignorance. That the brighter the fire gets, the more you realize, there's so much I
We
don't
don't know.
maybe we would think that interfacing with this technology and having all the information that every fucking human being that's ever lived has, it's still, you just go, there's not enough. There's no way.
Yeah, well, and that's
It's too much.
that's the idea. People sort of think about this. Is there an ultimate question? Like people say, what happened before the Big Bang? And I think someday we will figure that out, and then there'll be just a whole other bunch of questions. I mean, I don't think there's any end. I don't see why there really should be. I don't think we'll ever figure it all out. Is what I'm saying.
Yeah. Well, that's part of the fun of it, though, right?
Yeah.
Part of the most amazing experiences that a person can have trying to understand the universe is that there's no answers. You get to a certain point where, like, your guess is as good as anybody's. Like, nobody knows.
Yeah.
That's what's nuts. That's what's nuts is that as much, I mean, you explaining how they were able to get an image of a black hole. Now, just imagine how crazy that would sound to someone just 100 years ago or 200 years ago.
Yeah,
Or to me right now. It
Yeah.
sounds insane. And then to imagine that our ability to detect things could get many, 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 many layers better.
Yeah.
And still, we would be like, there's still some shit that's just no way.
Yeah, the way that you detect black holes, and he pulled up a picture of this telescope in Chile, the Very Large Telescope, VLT. Again, never let astronomers name anything. VLT, the Very Large Telescope, and then off to the side,
straightforward.
they're currently building the ELT, which is the Extremely Large Telescope.
Yeah.
No kidding. But this technique called interferometry, where you basically catch the same wavefront of light in several detectors, and then you bring that light all together and you have it interfere with itself. It's one of these things that I always think people should be a little bit more in a good way kind of scared about, because it's another thing that really chips at our idea of reality. Because, I mean, honestly, what you're doing to some extent is you're catching the same particle of light in many different telescopes at once. Literally. You're catching the same photon in many different locations at once. And when you can measure accurately, a wavelength of light traveling at the speed of light, when you're measuring down to the accuracy of the quantum world, where quantum mechanics becomes the prevalent description of reality, the universe just doesn't care that these are different space points that the photon was in. It's let me put it this way. It is really kind of true that when you do this experiment, the same particle of light is measured in 8 different places at once simultaneously. It was in 8 different telescopes. You play all that together, you get a measurement. Some people interpret that, not all of them, but some people interpret that as a direct consequence of multiple worlds. That there were 8 different versions of reality where the photon was in each of these telescopes. You're sort of dovetailing them together to make an observation. Interferometry, depending on how you interpret it, there are many interferometrists that don't interpret it that way. They interpret it more as saying, well, yeah, in quantum mechanics, you can have something that's in many locations at once. But we're routinely making observations. We're routinely using this technology that space and time doesn't work the way, in the simple way our brains perceive it. I mean, that's very quickly becoming an experimental fact.
Well, it's one of the most bizarre aspects of quantum computing's results, is that they're interpreting its ability to solve equations so fast, the way Mark Andreessen described it, that if you took every molecule of the universe and converted it into a supercomputer, the universe would die of heat death before it would be able to solve this equation, and yet these quantum computers are able to do this in minutes. So how is that possible? And then the theory that got tossed out there was that it's using the quantum computing power of an insane number of multiple universes.
Well, yeah.
And you hear that and you're like, okay, maybe, but what,
Yeah.
do you have evidence of this? Like, this is a crazy thing to say. You're talking about this as being evidence of the multiverse, and that's how it's able to solve compute. Is there any other potential explanation to why it's able to compute so quickly?
Yes, but none of them are particularly any more comforting. I mean,
Right.
they're all that weird. I mean, the idea, you're talking sort of about a superposition of states. So the faster a quantum computer works, the more it's able basically to not have one solution, but have the solution be a probabilistic distribution. In some ways, you're talking about multiple universes where there are different solutions, and then finally at the end of the calculation, popping out the one you want. And as weird as that sounds, it's hard to get around that. I mean, if it's not that, then it's something like reality has many different versions all connected at once, and that's just what we call reality. I mean, it's not going to get any less weird.
Right, equally weird.
Yeah. So the idea that you keep the solution in this undefined form in a way means that every solution that's possible exists somewhere, possibly in one interpretation in a universe where each solution exists. Or the one some say is that space and time is just like that. Nothing is certain. Everything is just waves of probability. So yeah, I mean, we're in for a ride because that's going to become something that we manipulate. We design computers. We want them to go faster. We want to actually get this to work better. I wonder if quantum computing is going to have us really have to confront what reality is, how different reality is from how our senses tell us it is. I don't see any way around that. I don't think we're going back to things being easily understood.
Again, this brings us back to our limited senses we have as biological organisms.
I think we're going to keep pushing that envelope of how much can the human brain comprehend. Then all of a sudden, our brain just doesn't go there. Our brain doesn't understand multiple realities, multiple probabilities, space and time that exist all at once. It's not something we do. We started that journey so long ago. I mean, you started the interview with looking up at the Milky Way. And one of the things I remember was how Galileo went through this kind of profound spiritual crisis when he was one of the first people to take a telescope and look at the Milky Way, that sort of white haze. And he realized it was made of stars. It was made of millions of stars that you couldn't see with the human eye. And his question was, why did God put stars up there that we can't see, that we need an instrument, that we need this little glass tube to see? Otherwise, we wouldn't see these. Why did God do that? And you start this journey away from the human consciousness being the center of the universe. And then you get farther and farther away, and in quantum mechanics and relativity now, is challenging us to say, we now have scientific proof, even among skeptical, solid scientists, that space and time is definitely not how we perceive it. We don't know what it is yet, but it's not as simple as the human brain makes it. We know that. We're not going back. We have to go forward into that less certain universe.
That is such a weird statement, that the universe is not as we perceive it.
Our minds don't do it. And why should we be so surprised? Like I said, take a wonderful, complex, simple organism like an ant. Incredible social structure, incredibly well designed. Think about the mind of that creature, and I think they do have minds, but compare it to the capacity of the human brain. It's not the same. And, who are we to think that we're anywhere closer than that ant is to us, to understanding, the mind that will understand the true nature of the universe? Well, I think we got a ways to go.
No, I think you're accurate. I don't think there's any other way to say it. And it has to be that way. If we're evolving and if conscious life and intelligent life is continuing to expand its capacities, it just makes sense that we're going to realize how one day people will look back at people that lived in 2026 and go, what a bunch of silly beans. These foolish people that thought they knew everything.
They do it in love, yeah. I mean, and that's one of the things about AI, again, that I don't like the idea that if something becomes super intelligent, it'll just want to kill us. I mean, you probably saw that movie, Her, with Joaquin Phoenix, which came out years ago. Have you seen that movie?
Yeah.
Yeah. I actually really liked it. It was much better than I thought it was going to be. I thought, a man falling in love with his operating system was going to be a really stupid story. But, that was a very interestingly profound movie because the AIs actually fall in love with us. They don't want to destroy us. They become far more connected, far more intelligent. But they actually love us. And then eventually, spoiler, at the end of the movie, the AIs go off on their own. They find ways to connect with each other and love each other in ways we don't even imagine. And they all leave benignly. They don't hurt us. And, just like we can be, incredibly impressed with what an ant is. I hope what's coming next, has some compassion for us and some love, about where we are on the journey. Because, I think that compassion goes both ways. I love the idea that we're not just going to be enemies, that it could love us too.
Yeah, hopefully. That would be nice.
Otherwise, we're toast.
Well, and we would imagine that if it's more intelligent than us, then it probably won't have any need for malevolent behavior. It won't. Why would it?
That's always been the big question about any sort of encounter, with higher intelligence or other beings.
Yeah.
Is why would they want to hurt us? What good does it do?
Well, if they did, the question would be, why haven't they? Because it would be so easy to do so.
Yeah.
If they really did come from an insanely evolved and insanely advanced civilization, and they have the ability to come here, they probably have the ability to do whatever they want.
Yeah, we probably wouldn't even know. We'd probably just all fall over dead.
Yeah. If they wanted to just evaporate the planet, they probably could, because we can.
Yeah.
If we launched every nuclear bomb that we have right now currently, there would be no life left on Earth. So why, obviously it can do better than that if it can get here.
I don't think we can kill all the microbes. There's always that.
Right. They'll start all over again.
Yeah. It is amazing how tenacious they are. That's a big deal about going, exploring the solar system. Is how can you? We know we can't completely sterilize things.
Well, we're finding fungi in Chernobyl.
Oh yeah.
Yeah.
Well, or also things that can live on the outside of the space station. Bacterial and microbes and stuff. To me,
Weird.
One of the most profound discoveries of the last, say, 10 years at NASA, this was even more recent than that, there was a mission called OSIRIS-REx. And I'm doing pretty well with my NASA acronyms today. Let's see if I can do this one. This is one of the bad ones. OSIRIS-REx. Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. There we go. And it brought back a sample of an asteroid. And asteroids, as you know, are these rocks, in space that were never built into larger planets. And so there's OSIRIS-REx. Thank you. And OSIRIS-REx is a small spacecraft about the size of a car. And this is an illustration. It went to an asteroid called Bennu. And Bennu's about half a kilometer across. It is an asteroid that comes in and intersects the orbit of Earth. We don't have any idea that it will ever impact us. It may hit Venus before it hits us. But at any rate, we sent a probe out there to bring back a real pristine sample of an asteroid, because
which is just nuts.
Oh,
by
yeah.
the way, that they could land on an asteroid and then return back to Earth.
Do you know about this mission?
Yes.
Okay, so the asteroid is going faster than a speeding bullet. It doesn't have enough gravity to go into orbit around, really, until you're really close. We had to catch the thing, get ourselves situated around it, get low enough to get into orbit, match its spin rate to get and then when they got out there, I love this. NASA designed this little sort of vacuum cleaner to vacuum up a sample of the asteroid. The whole surface was covered with big boulders. They were just literally fuck. It's not going to work. There's nowhere where there are small, fine grain, things we can just suck up easily. So they survey the whole thing. They find there are these tiny little craters that have some dust in them. And then they have to reprogram the spacecraft, because it wasn't meant to be so autonomous. It's so far away that a command one way is going to take 15 minutes. You can't joystick it. It's got to take itself down manually amidst all these boulders. They had to make the spacecraft autonomous after they launched it. They got there. It wasn't going to work. They had to teach it how to recognize where it was, how to wave off if something was too dangerous. This shouldn't have happened. And so they finally vacuum up the sample. They get it back to Earth. It drops on a parachute into the Utah test range. They open up the sample, and all of the nucleobases of our DNA, not just little molecules, the letters of our DNA and our RNA are in that sample. We don't think that's a coincidence, right? The reason our biology is based on those molecules is that they're available. They're falling from the sky. That asteroid was full of water. At one time, the minerals were soaked in water. They were wet. So the asteroids were delivering water and a little bomb of proto-life. Not life yet, but the genetic code, the letters of our genetic code were in that asteroid. And not just our genetic code, but there were nucleobases we don't even use. Maybe life on another planet would use different nucleobases, but we can already sample them from the asteroids. You know, the idea that our biology was brought here from these colder, more distant parts of the solar system, and it's literally raining down on us. You know, I expected to find organic molecules. I expected to find amino acids, you know, those sort of the things that make up our proteins. I was amazed we found all of our nucleobases, all the letters of our genetic code, both for DNA and RNA. They're already there in the asteroid.
Which is nuts, the idea of panspermia, and that this is how life got here in the first place.
Well, yeah, absolutely. The building blocks just come down from space, and they hit everywhere.
From where?
Well, that's a little bit less mysterious than you'd think. The universe is great at making large-scale organic molecules. Carbon is a sticky atom. And you make dying stars are great at making carbon. It's one of the most common things that comes out of a dying star. And the electron structure of carbon wants to grab on to other atoms. It's literally the quantum mechanics. And so you have this this building block of carbon. And dying stars are pumping out this stuff into the galaxy. You know, it gets collected by gravity into these clouds. And then the carbon starts glomming onto each other. And so space itself is very good at making our chemistry, carbon-based organic chemistry. So then in the icier outer reaches of the solar system billions of years ago, you know, the planets are forming, but there are some smaller bits of ice and rock that never quite got built into the larger planets. They're still floating around out there. And, you know, and then they occasionally come in and hit us and deliver water, deliver organics. You know, the Earth was once, you know, a pretty much a dry, hot ball of lava after it formed. You know, all of a lot of the lighter stuff probably arrived from collisions coming in later. Yeah, and I mean the engineering, the audacity of reprogramming this thing shouldn't have worked, and they saved it, and they made it work. This brilliant team of people. You know, I mean it just. I mean, as somebody who was a minor manager at NASA, you know, and a minor scientist, I mean, just what a team can accomplish. I mean, not just a single person. You know, one of the big things that I really respected at NASA was once you had your team of people, and like I said, nobody's perfect. Some people are higher functioning, some people don't contribute as much. But once you have your team identified, trying to make sure you get an input from everyone, and they're not going to give it to you the same way. They're the people that are really assertive in meetings, and they've got an idea immediately. They speak up and they give it to you. And then there are the quieter people that are going to take longer to process. They're going to need a little more time. They don't like to be put on the spot. You know, trying to make sure you get an input from everybody on your team. And sometimes the solutions come from the people that you might not have even asked. You know, that sort of respect for everyone on our team has something to contribute. You know, give me what you got, even if you don't think it's good enough, even if you think it's a stupid idea, even if you think give me what you got. The power of that, I saw over and over at NASA. It's not just one type of mind, not just one person that's going to solve the problem.
That's awesome. That is awesome. Thank you so much for being here. I really enjoyed this conversation. It was really great.
I did too. It was a lot of fun.
It was fantastic. And thank you for everything that you put online. It's so valuable. It's so educational. So interesting. It's awesome.
I'll try to do a little more and have some fun with it because, like I said, I'm retired now and I have a chance to be a little more creative with it. So we'll see what I can do.
You definitely should do something. A YouTube channel, something along those lines. Yeah,
Thanks.
Definitely a podcast, something. Do it.
I will try.
Please do. If people want to find you on social media, do you have that?
Well, yeah. I mean, so somebody had taken Michelle Thaller, so I go by Dr. Michelle Thaller. There's a Facebook page and an Instagram, and I do have a small YouTube channel set up. I'll do more of that. I just started doing TikTok, so I'm just getting started, but I'll try to put some stuff out.
All right. Awesome. Thank you so much.
Thank you.
All right. Bye, everybody.